Hey YouTube, so this video is a combination of my earlier videos on PyTorch techniques with some extra addition which was not there previously. So hope you enjoy it. Let's start. Yo, this is Rohan and very welcome to my channel. Hope you enjoyed this video and don't forget to subscribe because I'm uploading 5 to 6 videos each week, and over the next couple of months I will focus on machine learning's application in finance, trading, stock analytics and crypto. So enjoy and let's start. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, I will talk about weight decay in PyTorch while building a neural network. So first, the definitions. So weight decay is a regularization technique by adding a small penalty, usually the L2 norm of the weights, to the loss function. And that's the formula we see at the top, that is loss. The resulting loss will be equal to loss plus weight decay parameter multiplied by L2 norm of the weights, and this is a mathematical representation of the same formula, that is loss equal to error, that is original loss, plus these L2 norm of the weights, which is expressed as a lambda, which is a constant and hyperparameter, multiplied by all the weights to its squared. So that was a loss. And then for the formula for updating the weights themselves, this is what we use under weight decay. That is weight at t plus 1 equal to weight at t, that is the previous weight, minus learning rate into gradient of weight minus weight decay into the original weight. And this weight decay is the decay factor, which is the same as lambda in this expression, and it is a hyperparameter which needs to be tuned and given a proper value for the best result. Now let's just concentrate on this expression, which is the same as the top one, that is loss equal to error plus the L2 norm of the weights multiplied by the decay factor lambda. So let's break down these L2 regularization. So we have a loss function. Now we add the sum of the squared norms from our weight matrices and multiply these by a constant denoted by lambda. This lambda here is called the regularization parameter, and this is another hyperparameter that we will have to choose properly. And if we set this lambda to be relatively large number, then it would incentivize the model to set the weight close to 0, because the objective of a stochastic gradient descent algorithm is to minimize the loss function. And remember, our original loss function is now loss plus this whole amount. So lesser this amount will be, my loss also will be less, and that's the whole purpose of SGD algorithm. And to make that less, the algorithm will try to make this expression low as well. And so if we have already have chosen a high lambda, then the algorithm will choose a very low weights so that this whole expression become low, and that's when the algorithm will be incentivized to make these weights as close to 0 as possible. And why do we use weight decay at all? Mainly 2 points. That is to prevent overfitting, and the second is to keep the weight small and avoid exploding gradients, because the L2 norm of the weights are added to the loss, and each iteration of your network will try to optimize or minimize the model weights in addition to the loss. This will help keep the weights as small as possible, preventing the weights to grow out of control and thus avoid exploding gradient. And how do I use weight decay in PyTorch? Simple. It's already been implemented in the torch.optim module. So we have SGD and Adam here for this example, and you just need to, when you define optimizer that is using torch.optim.sgd or torch.optim.adam, there is a parameter called weight decay, and that is some value that you have to decide. You have to give because it's a hyperparameter. So here, for example, I have given 1e minus 4 for both SGD and Adam, and that's all you have to do in PyTorch to apply weight decay. Now, when you apply your weight decay to your optimizer like this, by default, it applies the weight decay factor to all the weights in the network and also all the bias terms in the network. And here lies an important fact that some people think that weight decay factor should not be applicable on the bias terms because these parameters are less likely to overfit. Also, many people think that the decay should also not be applied to parameters with the shape of 1, meaning the parameter is a vector and not a matrix, which is quite often the case for normalization modules like batch norm, layer norm, or weight norm. Hence, to solve this problem, we have a way indeed, because now PyTorch provides a way to get the named parameters from a network. So we can get a name along with the parameter value for your neural network. And for standard layers, biases normally are named as bias. That is, each bias layer will have the string bias appended to it at the last. And so combined with the shape, we can create two parameter lists, one with weight decay and another parameter list which does not have a weight decay, and then apply our weight decay factor accordingly. Let's quickly check out an example of that, what I mean. So I just want to check that how to get the parameter names with the help of named parameters, and then I can build a function to apply weight decay based on those named parameters what we just discussed. So I am just pasting some basic boilerplate code here with torch vision. I have my model defined as models.resnet pretrend equal to false, and I'm just printing it will be my model dot named parameter. So I'm just printing these named parameters and let's see what does it gives me. All right. Yes, it just gave me all these names of my model, which is a ResNet 50 with pretend false. So as you can see that I have all these names very properly defined. So all my bias terms will have a bias string at the end of it. So conv1.weight, bn1.weight, layer 1 0, conv1.weight similarly. So I can clearly see that all these bias terms I can definitely get from these names, from the list of names. So now that's what I'm going to do. There will be a single function to apply the weight decay factor based on these names. So some names, that is some parameters in my neural network will not be applicable for weight decay factor and some others will. So let's do that. So combing through some of the PyTorch related forums and GitHub, I got one function and I modified it very slightly. And here is this function, custom weight decay. So all this function will do is add the weight decay or not based on the names of the parameters. But before understanding this function, just quickly check out documentation in PyTorch, official documentation, what they are talking about per parameter options. So in this here, the documentation mentions that how you can control various things on a per parameter basis in a while implementing optim.sgd, or for that matter any optimizer. So what it says is optimizers also support specifying per parameter options. To do this, instead of passing an iterable of variables, pass in an iterable of dict. Each of them will define a separate parameter group and should contain a params key containing a list of parameters belonging to it. Other keys should match the keyword arguments accepted by the optimizers and will be used as optimization options for this group. So this is the dict that this is here talking about. So I have to have a params key, and the other keyword argument should be matched what the optimizers can take. For example, here for optim.sgd, for the params I can pass model.base.parameters. That means the model's base parameter will use the default learning rate of 1e minus 2, but here for the second line, I'm capturing model.classifier.parameters and passing a learning rate of 1e minus 3, meaning that the model.classifiers parameter will use a learning rate of 1e minus 3 and a momentum of 0.9, which will be used for all parameters. All right, now with this, let's check out this function. So all this function is doing, first it is just having two lists, decay and no decay, which will hold all the parameters that will have decay applied and no decay applied. And then I am just looping through the net dot parameters, and net is my argument. So if not params dot requires grad continue, that is, this is the frozen weights, and otherwise if len dot param shapes equal to 1, so this is my main condition based on which I will not apply the weight decay factor to those parameters. So if len params dot shape equal to 1, which that means it's a vector and not a matrix, or names dot ends with bias, that will capture all my bias terms in the network, and also any other name that I can pass as part of this argument skip list. Then if this condition is satisfied, I will add all these to my no decay dot append. So no decay list will hold all these parameters. Otherwise, the rest of the parameters will be held in the decay. And then I'm just returning a dict format of list, because remember the documentation said I have to pass a dict, so that should have a params key. So that's why I'm having a params key here. To that I'm passing no decay weight decay 0. That means all these no decay params will have a weight decay of 0, and otherwise other decay params will have a weight decay of L2 value, and L2 value is just a hyperparameter that you can decide upon. And then to apply this function, it's just simple, just invoke this function, pass it as an argument, pass it your whatever network you are building, and the learning value, L2 value is just a number that you have to decide. Here, for example, I'm choosing 2e minus 5, and then so then this param can be applied to my optimizer like this, that is torch.optim.sgd, that will take the params, and that will have this output of this custom weight decay function, and the learning rate will remain whatever you decide to choose. So this example was about disabling the weight decay factor for some layers. So let's name it accordingly, this cell. So this cell just did that, and next I am going to check that how exactly my weight decay factor actually works. So I need to see some evidence that the weights are reducing when I am applying weight decay. So let's do a very simple and quick example. And I got a very simple piece of code from PyTorch forum showing exactly how the weights will be smaller when I invoke the weights decay to my network. And this is that code. So let's check out this code. I don't need my imports already there at the top. I don't need that. So I'm just creating some Numpy array as random weights, and then creating a torch.tensor from those Numpy arrays, so that I can just pass this to an actual network and optimizer. So xtorch and weights.torch are those random weights, and then I am creating an optimizer, SGD optimizer here in this line, torch.optim.sgd. To that I'm passing this weights torch that has been randomly created. LR is my LR that has been defined earlier, and y torch will be just the matrix multiplication between my x torch and weights torch, that is the x values and the weights of them. And loss I'm defining to be y torch dot sum, and then the standard 0 grad backward and step to do a gradient, that is a back propagation, and that is this step will actually update the weights, so that I can see the effect of using my weights decay. So first I am printing here in the original weights. Actually this line should go here. So there are three sections of this code. The first, I'm just printing the original weights as it is, and then I'm doing this little SGD optimizer, passing the weight decay to be equal to 0. And then the same code like this, but here I'm using weight decay equal to 1. So here I'm taking the same weights torch, which is torch.tensor weights.weights_np requires grad equal to 2 true here, and then creating the optimizer, torch again, torch.matmul matrix multiplication loss, and everything else remains same. And now I'm again printing one weight decay that will be my weight torch. So what I want to see ideally is that when I use weight decay is equal to 0, then I get a set of weight values, and that will be slightly larger than when I'm using weight decay equal to 1. That means when I am actually bringing in weights decay factor, my weights will be reduced compared to their previous values. So let's just run this code and see the output. All right, this is my original weight tensor. This is my 0 weight decay tensor. This is after resetting, and weight decay tensor, 1 weight decay tensor is here. So just compare this tensor with a 0 weight decay tensor. So as you can clearly see, whatever values we got for our 0 weight decay tensor, that is reduced in the 1 weight decay tensor, because here for this result the weight decay factor has been applied on all the weights. But here, because there was 0 weight decay factor, no weight decay factor was applied. All right, so that was that's exactly what was expected for to be seen in this case. Meaning that's exactly what's one of the motivation of bringing in weight decay to a neural network, that it keeps a weight small and avoid exploding gradient. What we discussed earlier, that why do we use weight decay at all? To prevent overfitting and also to keep the weight small and avoid exploding gradient, because the L2 norm of the weights are added to the loss. That is here L2 norms. This is the L2 norm of the weights. So now my SGD algorithm will reduce this whole loss, and to do that it will reduce the weights, because so when I give a lambda to it, because the whole purpose of SGD algorithm to reduce the whole right side expression. And now that I have these weights, by reducing them I will reduce my loss, and in thereby I will the whole neural network will avoid exploding gradient. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in the last video, I talked about label smoothing in deep learning and the theory behind it. And in this video, we are going to implement label smoothing in cross-entropy-loss with PyTorch. And if you have not seen the previous video, I will give a link in the description of this video. Please see that, because that's kind of the prerequisite for this video. So just to give the background, that label smoothing in a nutshell is a way to make our model more robust so that it generalizes well, and by doing this it avoids a problem of overconfidence. In essence, label smoothing will help your model to train around mislabeled data and consequently improve its robustness and performance by bringing in some noises into your training process. So this is a formula for label smoothing cross-entropy loss, and what we do is that we bring in a small value, a number between 0 and 1 called this epsilon, and then multiply that with the cross entropy, and here CEI and CEJ they represent the cross entropy of X. That is, both CEI and CEJ is the cross entropy of I and J respectively, and which means that it is a negative log probability. And in the second term, I am dividing this whole expression by n as well, and the first term I'm just multiplying the cross entropy with 1 minus epsilon. So this is the below one is just the same expression, just represented in another form, that I have the 1 minus epsilon, and then instead of the cross entropy here, I'm just showing the actual log expression of that, because this is a negative probability here. And similarly here as well, epsilon and the negative probability whole be divided by n. So label smoothing is designed to make the model a little bit less certain of its decision by changing the target a little bit. And what I mean by changing the target is that instead of wanting to predict 1 for the correct class and 0 for the others, we ask the model to predict 1 minus epsilon for the correct class and epsilon for all others. And here epsilon is this small number, small positive number indeed, between 0 and 1, and this n, capital N, is a number of classes. And now we are going to implement this formula from scratch in a label smoothing loss class in PyTorch. And this is that class, label smoothing loss, which will implement the formula from scratch. So I have 4 methods inside it, and the initializer, that is the init method, reduce loss, linear combination, and forward. And all my logic of this formula will be inside these forward method. So first I'm initializing some of these variable, that is epsilon, all our arguments to this class, epsilon, reduction, and weight. And then reduce loss. This will just define how my the mean or the sum will be calculated as given the loss. And linear combination is the method which will actually implement part of this formula, that is ignoring n. The rest of these formula will be implemented in my linear combination. So I have self ij, and return is just 1 minus self dot epsilon multiplied by I plus self dot epsilon multiplied by j, the second argument. And if you match this with this formula, it is exactly this: 1 minus EPS into cross entropy I plus only the epsilon into cross entropy j, and ignore the n for now. That will take care of that inside the forward function. Alright, so that's my linear combination. And then forward, initially I'm just keeping an assert statement here to limit my epsilon value between 0 and 1. It cannot exceed this range. And then self.weight is obvious, self.weight to predict.tensor device, and predict tensor is an argument to this method, which will be a tensor of all the predicted values. And then number of classes is just from the size you take the last dimension. -1 actually means the last dimension from a tensor. And log predicts, this is my log softmax. Of course, this f is what I have imported at the top. 1 second. Yeah, torch.nn.functional as f. That's my functional module of PyTorch. And from that functional module, I'm just invoking log softmax. It will invoke the log softmax function on my predict tension, and dimension I'm again mentioning to be the last one. And then my this is log predicts, and then I have to calculate the sum of the loss, because remember, in the formula, for the second part of the formula, I have to calculate the loss sum over the loss. So that's what I'm doing here. Loss equal to loss dot reduce loss, which will have my log preds dot sum dim equal to -1, and log preds coming from here. Yes, and then I have to apply another function, which is my negative log likelihood loss. So that's coming from again the functional module, and this will take care of my this part of the formula, that is CEI, cross entropy I. This will be captured by this line here, negative loss likelihood. To that, I'm passing all the log predicts, all the log preds, and the target, which is coming from the argument. Reduction equal to self dot reduction, whatever it could be, mean. What are the acceptable values? Reduction, I think, yeah, sum or mean. Yes, so reduction is cell blood reduction, weight equal to cell blood weight, and finally I am returning the linear combination of them. That's where I'm implementing this formula. That is linear combination. To that linear combination, I'm passing negative log likelihood loss, and this loss is actually the sum of this calculates the sum over the tensor, and then to the second element, I'm dividing it by number of classes. Number of classes is coming from here. Remember the formula, we had to divide by these capital N, which represent the total number of classes. And yeah, so that's what I'm doing here, and this is my final return value from this function, from my this class label smoothing loss. And let's now test this function with some fake tensor. So my loss criterion, I am defining it label smoothing loss and giving an epsilon value of 0.5. I think default value I've chosen is 0.1. Yeah. So I'm giving a 0.5 epsilon value. Then my predict tensor, it's just a fake tensor I have created. This two-dimensional tensor. And then my target variable, again, it's just a 3-element vector 2, 1, 0, because here I have 3 rows. So I have to match that with 3 target variables. And so I have my predict tensor, I have my target variable. So I'm ready to calculate my loss, which is my label smooth loss. So to my loss criterion, I'm just passing these PyTorch variable, and within that predict tensor and my target, and that will give me my loss, which is label smooth. Let's run this cell. All right, I got the tensor as 4670, and that's my label smoothing cross-entropy loss. Now a quick word on this negative log likelihood loss, that is this one, f.nll loss. And what's the comparison with the cross-entropy loss of PyTorch? And the point is this, that if you apply PyTorch's cross-entropy loss to your output layer, you get the same result as applying PyTorch's NLL loss to a log softmax layer added after your original output layer. So here I'm applying these NLL loss after my log softmax. So from the after applying log softmax, I get these variable log preds, and then I apply the NLL loss on these log preds. So I could as well replace this NLL loss here with the cross entropy loss of PyTorch, and I would get the exact same result of 1.4670 as the output from this function. That's pretty much the relationship between cross entropy loss and negative log likelihood loss. That in these cases, that when you apply the NLL loss on softmax, it will give you the same result as it will with cross entropy loss. And the theory is that if we want to minimize the cross entropy loss, we need to minimize the negative log likelihood loss of the model. And cross entropy loss in many libraries typically calculate negative log likelihood loss and log softmax under the hood, just like in PyTorch. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn the dropout layer in PyTorch. So what is dropout in general? Dropout is a regularization method where randomly selected neurons are dropped from the neural network to avoid overfitting. And this is done with the help of a dropout layer that manages the neurons to be dropped off by selecting a frequency pattern. Once a model is entered into an evaluation mode, the dropout layer is shut down and training of the dataset will be started. So let's look at this image. With dropout, the training process essentially drops out neurons from the neural network. As we can see that some of these neurons, these marked as cross, they are dropped off. Note that the connections or synapses are removed as well, and hence no data flows through these neurons anymore in the network. But when neurons are dropped, they are not dropped permanently. Instead, at every epoch, the network randomly selects neurons that are dropped only for this time, and neurons that had been dropped earlier can be reactivated again during the future iterations. Now with some quick code, let's see the effect of dropout on training mode and evaluation mode. So my dropout has been defined to be 0.5. That's kind of the mostly used default value of dropout. And then I'm going to define a layer. That would be torch.nn.dropout. To that, I will pass that variable dropout and then see if my layer.training prints, so whatever it prints. It should print true, yes, and I got true. That means I am in the training mode, and now I will define input data, some fake input data. Let's do that with torch.ones. That will create a matrix of ones of 3 rows and 5 columns. Print input. All right, I got a 3 rows and 5 columns of tensor, and now I'll do layer input. All right, see, my initial matrix was all 1, and now after the first forward movement, I got two of them, and some of the neurons are now 0 because they have been dropped. And so that's how it works. And why I got true, because to make up for these dropping out of some neurons, the others will be multiplied by a constant, and this constant for this case will be 1 by 1 minus the dropout value, which for this case is 2. Let's do another forward pass by running this layer input code. All right, now even few more neurons were dropped, and with each forward pass approximately 50% will be dropped, and 50% neurons would be dropped because I have chosen my dropout to be 0.5. Now let's change the mode to eval mode, that is evaluation mode. Layer.eval, run this cell. All right, dropout 0.5 in place false. Now let's check what if the training mode has indeed been shut down. Layer.train, and that printed false. Remember, previously it was printing true when I was doing layer.training. Here I printed true. So now my training mode has been shut down, and I'm in the evaluation mode. And now check the dropout effect. So I again do layer input, and I got my original matrix all once. That was my original matrix here. So let's do another forward pass under the evaluation mode. Layer input. I got again 1. Let's do another time. Layer input. And the same result. That is, now there is no dropout because dropout has been shut down under the evaluation mode, and we can see that in the evaluation mode the dropout layer behaves exactly like identity mapping. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn how to get the total number of parameters from a PyTorch neural network model, and this is my function which takes a model as the argument. And let's start building the function. So I'm going to use pretty table to print my list of the models or the layers properly. Pretty table that takes a list models, and the second one is parameters. Actually, I can name it layers. This is a variable that I'm going to update with the total number of parameters and I'm going to use model.named parameter, which will return me the name of the parameters. Name parameter. named parameters. If not, and I'm going to make sure only the trainable parameters are returned. So I have to run a little if condition with requires grad parameters dot requires grad, then continue. Yeah, else params equal to parameters of named parameters. No, actually parameter would be my parameter dot I'm going to use numel, which is a PyTorch method, which will return me the total number of elements from an input tensor. Let's update this param table dot add row, and I'm going to add to this the name and params. Similarly, I am going to update the params total. Params total equal to param, that would be plus equal to params total equal to params. Yep. Param table. Okay, this is a slight spelling mistake here. Yep. And that's pretty much it. And now I can just print PRM param table, and also I can print something like total trainable parameters with gradients. That would be my this variable params total, and return me the param total. And then in the next cell, I'm going to check my this function if it's working properly. So I'm going to actually, I've already imported models, so I am going to pull a ResNet 50 model from my Torch Vision models dot net 50, and that would be pre-trained equal to false. And then all I have to do is to invoke that function count torch model. Count torch. What's the problem? Count this one, and that would take my model. Let's run all of them. And after running, I got this result: output exceeds size limit. Okay, but anyway, I got all my layer names and with the parameter names, and it cannot show right in this notebook because there are too many models. But total number of parameters is this. How many are them? 255,057,032. And if I click here, open in a text editor, yeah, here now I can see all the list of parameters. It really looks pretty. The pretty table has really worked here. And so these are all my model names. So for example, this is bias. All the bias terms will have this bias at the end of their name. And for example, layer 1.0 down sample weight. And this is, remember, this is Torch Vision's pre-trained ResNet 50 model. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will cover two topics: how to convert torch.tensor to NumPy ND array, and what is the relation between the ND array of a NumPy and a tensor in Torch. So first, to start with, I am defining a simple tensor that contains just two values, 1 and 2, and this tensor also has recurse grad set to true, which is a property of a tensor in PyTorch. And then I'm just printing it, the tensor, and also the type of this tensor, and this is what I get after printing. The tensor is 1, 2, recurse grad is true, class is torch.tensor. Now this tensor 1 I want to convert to a NumPy array. So let's do the obvious code that may come to your mind, that you just take this tensor and do a dot NumPy on this, and let's run and see what I get. And I got an error. It said can't call NumPy on tensor that requires grad, use tensor.detach.numpy instead. So let's just do what this error itself is advising, that use tensor.detach.numpy instead. That is, I have to bring in this new method called detach. And now this is my code. Just the addition is just this detach method, and then print the tensor and also the type of it, and running this cell. Now it ran just fine, and what I'm getting is that the type right now is np.nd array. So previously it was a torch.tensor. Now it has got converted to np.nd array. And how it happened? With this detach method. I called this detach method first, and then on top of that I called NumPy. Now here is explanation. That the point to understand here is the difference between a torch.tensor and np.nd array. While both objects are used to store n-dimensional matrices, torch.tensor has an additional layer which is storing the computational graph leading to the associated n-dimensional matrix. So these torch.tensor are designed to be used in the context of a gradient descent optimization, and therefore they hold not only a tensor with the numeric values, and actually more importantly, they also hold the computational graph leading to these values. This computational graph is then used with chain rule of derivatives to compute the derivative of the loss function with respect to each of the independent variables used to compute the loss. But the problem is np.nd array, what we are converting here, np.nd array does not have this computational graph layer, and therefore when converting a torch.tensor to np.nd array, you must explicitly remove the computational graph of the tensor using this detach method. Now another question that may come to mind, that without using the detach method, what exactly happening? Why does it break the graph to move to NumPy? Is it because any operation on the NumPy array which will not be tracked in the auto-div graph? And the answer is indeed yes. If I directly try to convert a torch.tensor to np.nd array, the new tensor will not be connected to the old tensor through a grad function, that is gradient function, and so any operation on the new tensor will not carry gradients back to the old tensor. So that's why I'm writing these detach methods. So writing this tensor.detach.numpy is simply saying that I am going to do some non-tracked computational computations based on the value of this tensor in a NumPy array. So detach will stop the tensor from tracking history by detaching it from the computational history, and to prevent future computation from being tracked as well. However, if you wish for some reason to use PyTorch only for mathematical operations without the backpropagation, that is without the computational graph or gradient calculation methodologies, you can use the torch.nograd context manager, in which case computational graphs are not created, and torch.tensor and np.nd arrays can be used interchangeably. Let's see with an example. Here, this is my example. So at the very top line, I'm just setting the context manager torch.nograd, which will stop the gradient calculation with, so my computational graph will not be created. That layer will not be attached to my torch.tensor. And now let's run this code. Otherwise, so except for this line, the rest of the codes is just simple, exactly what I did at the very first step, that I'm not using detach method at all. So I am just creating a tensor, and then I'm converting this tensor directly to NumPy without the use of the detach method, and let's see if it runs correctly. And indeed, so originally my tensor was a torch.tensor, as you can see from this line. It is output of this line, print type of tensor1, and then I converted this tensor1 to a NumPy, and I'm printing this type of tensor1 at the end. And now my original torch.tensor got converted to np.nd array without the use of the detach method, because I have torch.nograd context manager set at the top. So in this case, np.ndarray and torch.tensor, they are pretty much the same thing. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will understand cross-entropy-loss implementation in PyTorch, its relationship with Softmax function, and at the end, we will check that in PyTorch, cross-entropy-loss already includes the Softmax calculation within its definition. So to begin with, what is cross-entropy? Cross-entropy is a function that compares two probability distribution. The key thing to pay attention to is that cross-entropy is a function that takes as input two probability distribution Q and P and returns a value that is minimal when Q and P are equal. Q represents an estimated distribution and P represents a true distribution. In the context of machine learning classification or deep learning for that matter, we know that actual label of the training data, so the true target distribution P has a probability distribution of 1 for the true label and 0 elsewhere. That is, P is a one-hot vector. On the other hand, the estimated distribution output of a model Q in this image generally contains some uncertainty. So the probability of any class in Q will be between 0 and 1. By training a deep learning system to minimize cross entropy, we are telling the system that we want it to try and make the estimated distribution as close as it can to the true distribution. Therefore, the class that your model thinks is most likely is the class corresponding to the highest value of Q. And now, what is Softmax? Softmax is a function that takes a list of unbounded values as input and outputs a valid probability mass function with the relative ordering maintained. It's important to stress a second point about the relative ordering. This implies that the maximum element in the input to Softmax corresponds to the maximum element in the output of the Softmax. So let's check this example. I have an input image that goes through many layers of a neural network. Then from this neural network, I get an output. This is unbounded. That is, the number can be much higher than 1. And then these unbounded numbers goes through the Softmax calculation. And after Softmax, from the output of the Softmax activation layer, I get this bounded value, which is actual probabilities. And they always will sum to 1. And then the highest probability will be my true label. So the prediction from this is that this highest probability, that one will be classified as dog. And so basically Softmax just converted this probability to my target level, target one hot vector of 1, 0. So Softmax is not really a loss function. It has a very specific task. It is used for multi-class classification to normalize the scores for the given classes. By doing so, we get probabilities for each class that sum up to 1. Now coming back to PyTorch implementation of cross-entropy-loss, I'm looking at the official documentation and it clearly says that this cross-entropy-loss implementation includes the combination of log softmax and NLL loss, which stands for negative log likelihood loss. So the key point is that in PyTorch, it combines this class, this cross-entropy class combines nn.log softmax and NLL loss in one single class. So do not use nn.softmax function in the output layer for a neural net when you are using nn.cross-entropy-loss as a loss function. Let's quickly check an example. So this is a very simple, straightforward implementation of a neural network, and this deals with multi-class classification. So at the top, I am defining some of my layers within nn.sequential, linear, tanh, linear, and then I am using cross-entropy loss, and then optimizer. Finally, I'm running the epoch. So the main point here is that in my model definition, this nn.softmax at the last line should not be there. That's because the output from the network that is passed into the nn.cross-entropy-loss here needs to be the raw output of the network, also which is called logit, not the output of the softmax function, because the softmax will be already included within this cross-entropy loss of PyTorch. And that's exactly what we saw in here in this picture. That is, these logits from my neural network that needs to be passed to my cross entropy loss, not the output of the softmax, because these output from the softmax will be these bounded probabilities, and that calculation is already included in the cross entropy loss of PyTorch. And now I will actually go step by step to build the cross entropy manually and check that my result matches with the ones from cross entropy loss of PyTorch, so that I can actually verify that this cross entropy has the softmax calculation within it. So here I am in my notebook. I'm just importing torch and the torch.nn module. Then I'm creating a fake output tensor with torch.randn function, and this output tensor will be 3 rows 5 columns, and setting requires grad equal to true to make all my parameters trainable. And let's just run this cell to see the output tensor. This is my output tensor, 3 rows by 5 columns, requires grad equal to true. And then I am creating the nn.cross-entropy-loss object, and also creating the target vector by taking the argmax from the output tensor across dimension equal to 1, which means across the rows. Run this cell to check my target vector. This is 3, 3, 2. That's my target vector. And then I am calculating the loss, which will be my cross entropy loss. So to this I have to pass the output, that is the prediction, and then the actual target, that is a ground truth. Let's run this cell to see. Yeah. So this is my loss, 1.0450. It calculated based on the outputs and the targets and applying nn.cross-entropy. Now what I will do is I will just implement a manual cross-entropy loss. Entropy loss. And check that my manual calculation matches with what the number that PyTorch gave me. So first just check my output tensor again, that I have the original output tensor. Yes, I have. And then I am first going to bring in softmax function of torch to be applied on this output tensor. So I'll pretty much be applying my softmax to calculate my bounded probabilities from these unbounded values of the output tensor. And this is my code, softmax proba equal to torch.softmax, outputs x is equal to 1, that is across the rows. Run this cell, and this is my probabilities, that is these are normalized values, which is output of the softmax function. And all right, so this is a 2D tensor. Now from this 2D tensor, which is output of the softmax function, to calculate the cross entropy loss, I have to apply negative log on these tensor. So basically, my loss, that is a cross entropy loss, can simply be computed by taking the average of the negative log of the probabilities of my true labels from the softmax. And what is my true labels? Let's get back to our presentation. So this is a softmax, and output we got all the probabilities, and I just have to take the highest value of the probabilities. That's my true label. Now I have these 2D tensor, so from each of the row I have to take the highest value as my true label, and then apply negative log on that. And what do I mean by negative log? What I mean is that I have to pass these maximum of each row from the output of the softmax through this negative log function. This expression also means 1 bar, so the entire expression is minus log to the within the braces. I have to pass the softmax and take the maximum from each row, and this can be the same expression can be also written as 1 divided by log softmax and the maximum of each row. And this is because by the fundamental rule of logarithm, that is log 1 by a equal to minus log a, which means the logarithm of 1 divided by some number is equal to the negative logarithm of that number. So let's get back to our cell here, and the code for this will just be this simple line. My loss manual will, in this case, be this simple line. And what I'm doing here, all I'm doing from this tensor, that is Softmax proba, and I'm going through each of the rows and just taking the maximum value from these rows. So for example, for the first row, which is at the 0th index of this 2D tensor, my highest value is this one, 0.3719. So I get that value by doing this Softmax proba, and then 0 as a first dimension, 3 as a second dimension. Similarly, for the second row, I have to get the highest value, which is at position of here, this one again, number 4th position, that is 3 indexed. So I do Softmax proba 1, 3. And for the last one, I have the highest value here, 2965, and that is indexed at 0, 1, 2. So for the last one, I'm just extracting that value by 2 and 2, and then I'm taking the average of all these values, because that's how the cross entropy loss is calculated, that it's nothing but the combination of softmax and the negative log likelihood and taking the average. And then if I run this cell, I will get this value, tensor 1.0450. Let's see if we got the exact same value with torch implementation. And indeed, while we applied PyTorches in build cross entropy loss, we got the same value, that was 1.0450. And here, only change we did is I applied the softmax separately, and then from the output of the softmax, I took the maximum value of each row and applied the average on that. I mean the negative log probability, and then the average on the negative log probability, and I got the same value. So that shows what we were discussing at the top, that while using nn.cross-entropy-loss on a multi-class classification problem in PyTorch, you should not apply softmax as the last layer of your neural network. And for doing this little calculation, that is taking the maximum value from this 2D tensor, that is output of the softmax, I could have actually used a torch.max function. I did not really have to check each one of them myself. So something like this, that is max from tensor, torch.max, to the first argument you pass softmax proba, that is this tensor, and dim equal to 1 means across the rows. So if I want to, let's just check what this prints. Yes, so this will give me the max from tensor, will give me the maximum value, it will give me this tuple, the value and the indices, corresponding indices. So the maximum value for the first row is 3719. 3719, second row is 3945, and the third row is 2965. Yeah, so I can define some max row variables, something like this, taking from the output of torch.max, something like this. Row 1 max will be max tensor, max from tensor, and 0th index and 0 value. 0th index means I'm taking all these, because this is a tuple. Torch.max will return me a tuple, values, max values, and the corresponding indices. So that's why I'm selecting 0, that is to select the value array, and then from that I'm taking the 0 first and the second element, and then my same function here will look something like this. Let's calculate it again, something like this. So now I have, instead of the softmax 0, 3, etc., all these large things, I'm just passing row 1 max, row 2 max, row 3 max, dividing all of them by 3, and let's check if I get the same result. What happened? Oh yeah, I did not run all this cell. I have to run all this cell. Yes, I got the same value, 1.0450, exactly what I got here. All right, so now again, to summarize, always remember that do not use nn.softmax function in the output layer of a neural net when using nn.cross-entropy-loss as a loss function. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this quick video, I will talk about the lazy linear module of PyTorch and a very simple use case of this. And the important key points of this module from the official documentation is that in this module, the weight and bias are of torch.nn.uninitialized parameter class. They will be initialized after the first call to forward is done, and the module will become a regular torch.nn.linear module. The in features argument of the linear is inferred from the input.shape -1. This is the most important thing here. That is, the in features argument of this layer will be inferred, so I do not have to explicitly provide it. Let's quickly see an example. Let's look at this very simple neural network architecture here, which has mainly two layers. One is the conv layer here, and another one is the fully connected layer. And when we create a model, we have to calculate the size of the first fully connected linear layer. So here, as we can see, this feature x in feature, this would be the number of neurons in the first linear layer, and I am supposed to input it here. Now the question is, how do I get this number? Do I need to keep track of the shape of the output tensor from all these layers? So figure that out here. We can definitely do that by implementing the formula. And that formula would be something like this, that output shape would be defined by this formula. This is a classic formula in a neural network, where I is the size of the input neuron, k is kernel size, p padding, and s equal to stride. But we do not want to do that. I want this number x in feature to be inferred by the model itself from this architecture. And that's where the lazy linear module comes to help. So what I can do here, just replace this nn.linear with lazy linear. So LAZY, and then take this one out completely because that will be inferred, and keep 512 as it is. That is all. And now these in features will be inferred, just like what the documentation said very clearly, that in the case of lazy linear, the in features argument of the linear is inferred from input.shape -1. And now another useful tricks when fetching pre-trained models from PyTorch image models module, that is TIM package. Let's see an example. So a pattern that we often see many people uses is this, that is, I'm creating a model with tim.create model and then supplying my model name, which is coming from another class named CFG, and pre-trained will also be defined somewhere separately outside this class. I mean, normally it's just true in this case. And then I define number of features, model.classifier, nn.identity, and finally these fully connected layer with where I define the in features and also the target size. And here as well, lazy linear can help to make it more compact and make it more reusable. Let's see how. So in this case, I can replace all these individual lines of self with these lines. Self.model, then I do create model usually, and CFG.model name, pretend to number of classes 0, all works fine. Then in self.fc, I bring in lazy linear, and here I just input the target size, which comes from the CFG class, which is defined somewhere else outside of this class, and from there I get a target size. And what exactly is happening in these lines are that when I mention num classes equal to 0, it tells these tim to return a pooled feature vector. The size of this vector can vary between architectures. For example, if I am using ResNet 34, this will be 512. If I'm using EfficientNet B0, this will be 1280. And then the point is, lazy linear will determine what the input size is and create a normal linear layer accordingly. So this will allow me to quickly switch architectures. For example, here, for if I want to change the architecture each time, I have to mention quite a few things separately. But here, lazy linear model will help me quite a lot in inferring the in features for me. And also this model name come from a separate configuration file, for example a config file or something like that, which will make this kind of structure more reusable. Now, important point to remember again that the weights and bias for under the lazy linear will be of the type torch.nn.uninitialized parameter class. They will be initialized after the first call to the forward function is done, and then this module will become a regular torch.nn.linear module. And obviously the in features argument of the linear is inferred in this case. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn three things: the input shape of a tensor into the convolution layer in PyTorch, the input shape into the fully connected linear layer, and thirdly and most importantly, the conversion of your tensor that you have to do while moving from the last convolution layer to the first fully connected linear layer. And I would say this third point, that is the transfer from the last convolution to the first linear layer, is where the most confusion comes for beginners in neural network. So let's jump in. And first, I'm looking at the official documentation of linear layer in PyTorch. And so it says the torch.nn.linear, it takes in features and out features. This is where you have to define the two variables here. In features, size of each input sample, and out feature, size of each output sample. Now let's look at conf2d documentation of PyTorch. So here torch.nn.conf2d, and it takes in channels and out channels as the first two arguments. And in channels here means the number of channels in your input image, and out channels is a number of channels which will be there after the convolution is applied, that is at the output end of this particular layer. And important thing to remember here is that these in channels or out channels for the conf2d is completely different thing compared to the in features and out features of a linear layer. Let's quickly do a quick example for the linear layer. So here I'm creating a fully connected layer using nn.linear. I'm passing in features to be a number 4 and out features to be number 3, bias false. Meaning I am defining a linear layer that accepts 4 input features and converts them into 3 output features. And for this conversion, we know that weight matrix is needed to perform this operation. But where is the weight matrix? Where am I defining it? The answer is PyTorch linear layer class uses the number 4 and 3 passed in the constructor to create a 3x4 weight matrix. Let's quickly check that that's exactly what is happening in the source code. So I am just going to this GitHub PyTorch source repository, and I'm looking at linear.py line number 79. That's where my linear layer init function, that is a constructor, is defined. And if you quickly check, this is my linear.py, and this is the class linear, and then within it first comes this underscore init method, and that's where these weight creation calculation will be done. And as we can see that self, in features, out features, and then there is a self.weight. This line is where the weight is created, and self.weight equal to parameter torch.empty, then out features, in features, and also it takes a variable number of kwargs argument. So that's how in this line inside the constructor of this linear layer, the weight matrix will be created to do my conversion from these in features to out features. And now, before deciding on the shape of in features or in channels of the tensor that will be fed into these layers, let's quickly revisit 5 different shapes of tensor that we will be dealing with in our conv 2D and linear layer. So here is an example, torch.size, for example, 16. This is a scalar. That means it's a one-dimensional tensor. This 16 probably is denoting only the batch size. This is used mostly for target labels, vectors or target predictions. Then I have a two-dimensional tensor, torch.size, for example, 16 to 56. Here they represent batch size, number of features, and this is the form that is used for the first layer in nn.linear, that is my linear layer. And then I have a three-dimensional tensor. Here 10, 1 and 2048, I have taken these numbers as an example, and here 10 represent batch size, then I have channels, and then number of features. And this normally is used in conv 1D and sometime also in recurrent neural network. And then I have the very well known and most popular four-dimensional tensor, 16, 3, 28, 28. These numbers are taken as an example. Here 16, the first one represent batch size, then channels, then height and width. And remember, this is the way PyTorch determines the shapes to be fed into a conv 2D layer. So in PyTorch, the first dimension is batch size, then channel, then height and width. This is the most important thing to remember, because accordingly you have to reshape or resize your tensor for various layer. And this structure is specifically for PyTorch. In TensorFlow, it is slightly different. And I also have an example of 5D tensor. This is rarely used because here I have an extra dimension depth, and that's used for conv 3D. But in our examples for this video, we will be dealing with mostly this four-dimensional tensor and the two-dimensional tensor. Now let's feed an image to nn.linear layer. Let's say I have an image of shape 28 by 28 here, and that is represented in an image vector which is of shape 28 by 28. Now this 28 by 28 pixel image can't be input as 20 as a vector, something like this 28 comma 28. I cannot input this tensor to a nn.linear layer. This is because the nn.linear will read it as 28 batches of 28 feature length vectors. That is, the first dimension will be taken as a number of batches by nn.linear layer, and the next dimension, this will be taken as a number of features, since it expects an input of batch size by number of features. That's how linear layer work. That is, linear layer expects one second, let me take it. Linear layer expects image to be fed into its layer in this format, that is batch size, number of features. So how do I feed my 28 by 28 image to a linear layer? And so to do that, I have to reshape my image vector to this form, that is batch size and number of features. And I can do that with the PyTorch's view method. And this is the kind of code that you have to use, and you will see this classic line of code many times in any neural network architecture, that this image, this vector here, is your original image vector, which can be of any size, 28 by 28, 32 by 32, or whatever, 256 by something else. Then you apply view on that. The first dimension is batch size, because we already talked about the first dimension necessarily need to be batch size for nn.linear. And then you pass a -1, which means that by passing the -1, basically I am telling PyTorch, you figure out this other number, that is the second dimension, for me please. And because the first is fixed, first has to be batch size, whatever the layer it is, how much ever deep your neural network is. For a linear layer, first dimension has to be batch size, and the second dimension I am putting -1 to my view method, means PyTorch will determine it for me. Let's actually see an example to then everything will be cleared. So for this example, I am defining a batch size equal to 1, and I am actually simulating a 28 by 28 pixel image, that is grayscale pixel image, with these vector. That is, input image is a vector which is defined as torch.randn, and I'm passing 1, 28, 28. That is one channel, 28 height and 28 width. So this input image just will be a vector that will have an image. Let's run this cell to be clear. Yeah, so my torch.size is 128 by 28. So this is my input image. But as we just discussed, I cannot use it directly into my nn.linear. So for that, what I have to do is reshape it by this line of code. That is, I am transferring or converting my input image to this view. That is, first dimension is batch size, which I have already defined to be 1, and the next dimension I'm putting it to be -1. That means PyTorch will decide or infer it for me. This is an inferred dimension, and let's see now what it prints. All right, now I got 1 by 784. That's exactly what I needed for nn.linear layer. So what it did is kept the batch size to be 1 because that's what I have defined at the top. And the next dimension, second dimension, is just 28 multiplied by 28. That gives me 784. And that will be, this vector is completely ready to be input into my nn.linear layer. Let's do that now. And with this line, I'm creating a linear layer with 784 and 10 as my in features and out features. Remember the documentation? We saw linear layer take in features and out features as the first and second dimension. That's exactly what I'm doing here. 784, that's my in features. And now I want to this fully connected linear layer, I want to feed my input image, this input image, and we will see that if it builds correctly. So I'm passing in this simulated input image to my fully connected layer by just doing this line of code, fc, and then within braces, input image. This input image is coming from here, which we already saw is of size 1 by 784. And now run this cell, and it ran properly. I got the output size as 1 by 10. 10 here, again, it is out features, which is like, in this case, you can say this is a number of output features after this linear layer. And now I'm going to see an actual example given in the PyTorch official documentation of implementing a full neural network. And this is this page where this is a tutorial page, and they are implementing this particular network. By the looks of it, looks like this is LeNet 5. All right, that is not important. The important is how they are implementing it and how they're calculating the input shape at various stage of the network. So basically this network here, the input is a 32 by 32 shaped input images, and it looks like it's a grayscale image. Then I have a convolution layer where it is converting it to 6 channel and 28 by 28. Then I have a subsampling, then another convolution, another subsampling, finally a fully connected linear layer, and then couple of more layers, and then I have the final output of 10 classes. So what I'm going to understand now, that how they are calculating, how they're implementing this architecture by calculating the input shape at various stages. So let's look at the code that they have used. All right, so this is the code, that class net, this whole class here, that is this whole class will implement this architecture. So let's see. So initially these at the first stage I have a conv 2D layer. So they are giving 1 6 5. Here 1 is my in channel, 6 is my out channel, and 5 is here stands for a kernel size actually. And because it's a 5 by 5, that is a square metric, so we can actually select a single number. They are very clearly saying it. 1 is input image channel, 6 output channel, 5 by 5 square convolution kernel. Then I have another convolution, 6 16 and 5, going by the same argument definition. And after these two convolution, I have my linear layer. Now this is the important stage, that this was my final convolution layer and this is my first linear layer. And let's look how they are defining these shapes here. So the final convolution layer has had these in channels, out channels. For the linear layer, we already know from the documentation, again it takes in features and out features. Now let's understand. They have selected the in features to be 16 multiplied by 5 multiplied by 5, which gives me 400, and then 120 as out features. Now the question is, how they decided on this number? Why exactly 400? Let's understand that. Now to understand this number 400, for the first linear layer in here, that is 16 into 5 into 5, I have to understand how a tensor needs to be reshaped while moving from conv 2D layer to a linear layer, and there is a rule for that, and the rule is this. First, conv 2D will output a 4-dimensional tensor, but nn.linear layer will only accept a 2-dimensional tensor. So I cannot directly feed the output of the conv 2D layer to my linear layer. Hence, I have to make a reshaping of the tensor here. So this is the rule. When transitioning from a convolutional layer output to a fully connected linear layer, resize your tensor from 4-dimension to 2-dimension using view method. And of course, instead of the view method here for the reshape, I could use some other method like flatten or even reshape, because the ultimate goal remains the same, that is to reshape my 4-dimensional tensor, which is output of the conv 2D layer, to a 2-dimensional tensor to prepare my data for feeding into the linear layer. So in this particular case, for this example in PyTorch tutorial, they have used the flatten method to do the reshape mechanism. Of course, later in a second, I will implement view instead of flatten and check the numbers are working. So basically under these underscore init, which is a constructor, my model is defined, and then these models are invoked one by one within the forward method. So basically in the forward method, you have the input from one model coming from the output from the previous model. So for example, x is output from my conv1, and then this x goes to the input of conv2, and then I do flatten. So after conv2, I get an output x, then I flatten this x, then this x goes to the input from my fully connected layer, and again my the result of this fully connected layer x goes to the next fully connected layer, and so on. So what I have to do to check these, how this 400 is coming, I have to include a print statement in my forward function, and before applying this flatten, let's do that in my VS Code. So my last convolution layer ends here, and only after that I'm applying flatten. So I have to include my print statement over here. So I just included a print statement by printing x.shape, and let's run this cell. All right, I get a 4-dimensional tensor here, 32, 16, 5 by 5. Here 32, just as we discussed in PyTorch, and the first dimension is always the number of samples in a batch. So this is that number. And then I have my channel, and then I have height and width. So batch, channel, height, width. And now I am going to check that this 4-dimensional tensor is being reshaped to a 2-dimensional one before feeding that to my fully connected layer. And so that's the job of this flatten, that this is doing the reshaping. So let's include a print statement here, that will be shape after my flattening. So I just included, I'm just printing this x.shape after the flattening as well, and run this cell again, and indeed my tensor now is a 2-dimensional one, 32, 400, and you see this 400 number. That's how I'm including it here, that is as the input in features for my linear layer, that is 16 multiplied by 5 gives me 400, because after the flattening, after the reshaping, that's the size I'm getting. And 32 here again represent the batch number. Remember that never changes throughout the layers between all the layers, how much of a deep that is your neural network architecture, the batch number remains the same. In this case, it was defined to be 32. So now that's how I'm getting my 400 after this reshaping. And this is a kind of pattern you will always see in mostly all neural network architecture with PyTorch, that after the last convolution layer you will get a 4-dimensional tensor, and then you have to reshape it to a 2-dimensional tensor by use of either flatten or torch.view or torch.reshape. And so just like we thought that I am going to replace this flatten with a view, so exactly the similar job I will do with the view, because in mostly all public GitHub repos and Kaggle, etc., you will see implementation of this torch.view method here. And that the job that they are doing is the same. So here as well, I'm actually flattening or reshaping the tensor. And the first dimension, I am keeping it as batch, because x.shape 0, that represents a batch number. We already saw that x.shape gives me, x.shape gives me this vector, this array or list, and the first element is 32, and that's why I'm keeping x.shape 0 to my view, because I always want to keep the batch as constant. And then -1 just means that I'm telling PyTorch that decide the second dimension for me, and then PyTorch will do the required calculation. And so basically means this second dimension will be inferred based on my input shape, and after considering the first dimension has been fixed at 32. So with this, let's run this cell. And right, I got these working again. So before the reshaping, I had a 4-dimensional tensor, and after the reshaping, I got again the same 2-dimensional tensor of 32 by 400. And all right, and so that's how it is decided. And if you are thinking that okay, so I got these number to be 400, and how come this 120? This 120 is out features, and that is coming from the architecture. So the architecture that this code is implementing is this, like we saw. Yeah, so this is architecture, and by the design of the architecture, after the first fully connected layer, the output of this first fully connected layer is 120, and that's why they have used 120 as a second argument to nn.linear, because this is just coming from the design of the architecture. So now let's just also check the final output from this network. So just comment out this to print line, and so here I am just creating a net object from this my net class, and then I am defining input variable. This is just to simulate an image to be an input image with torch.random, and 32, 1, 32, 32, they're all again batch number, channel, height and width. It is a black and white image that this architecture is about, and grayscale image. That means that's why I'm passing the channel as 1 for the input image, and the output will just be net, and to the net I'm passing input. And let's just check my output.shape. Yeah, so output is 32 by 10. Here 10 means the final outcome from this architecture again is 10 classes. As we can see, output is 10 target classes, and that's exactly what I'm getting the output as. And 32 here again is a batch number. Let's just see another example, another random neural network architecture example. So this architecture I got from somewhere from the internet, and here again this code is just implementing a neural network, and that neural network is consisting of a conv layer and then another conv layer. Of course, there's a max pool within these two conv layer, and after these two conv layer I have a linear layer, and then lastly a softmax layer. And now let's see again that why. So the first conv layer takes 3 by 16 by 3, and here it's a color image that we are talking about. So the channel number is 3, and The key point that I want to point out is that my first conv layer ends here, and there my input in channels, out channels are shaped like this, 16, 32, 3, and then my self.linear layer, that is the first linear layer, I'm giving the in features to be 32 multiplied by 7 multiplied by 7, and C remains number of classes which has been defined at the top, C equal to 10. Now why is this? Where from this neural network got this particular number? How come no other number? How come just this? That is, if you multiply this number, you get 1568. 1568. So why the in features is 1568? And again, you can do that by just including, just like we did in the previous example, include a print statement in my forward function, because within the forward function is where I am invoking all these layers. I'm getting the input from one layer and taking the same input for my next layer, and thereby at each layer, at the end of each layer, I can check the shape of the previous layer. And then normally when you are beginning in neural network, and even if you are a seasoned practitioner, it's normally a good practice to check your shape of your architecture by printing the shape at the end of various layers. So I'm going to do this thing here, print shape of x before linear layer, x.shape, and now if I run this cell, and again this cell, I'm doing exactly the same thing. First I'm defining my entire neural network architecture within this class, and then I'm invoking this class. I'm creating a dummy data here. This is just simulating an input image. 32 is batch number, 3 is number of channels because it's a color image, and 64 by 64 is height by width. And then I am invoking this net, that is the CNN C classifier, with this input image. Let's run this cell. All right, and you can see that shape of x before linear layer printed 32 by 32 by 7 by 7. Here again, in PyTorch, the first dimension is always batch number. So my second, these three dimension 32 by 7 by 7, these needs to be combined. This needs to be together to before I can pass this tensor to my linear layer, because this is a 4-dimensional tensor, but linear layer I can only pass 2-dimensional tensor, and hence this line here, fc1, that takes this line here. I'm using view to the view, so I got my x here to that. From that x, I am using view to reshape it, and for the first argument to view, I'm passing x.shape 0, which will give me 32, because batch I cannot change. It has to be, the first dimension has to remain batch always. And for the second dimension, I'm just including -1. That means PyTorch will decide it for itself, and they decided it will be 32 into 7 into 7, which is 1568. And that's exactly why for my designing of the architecture here in the linear layer, I am passing 32 multiplied by 7 multiplied by 7. I should also check the shape of x after here. Let's include a print statement here. Shape of x after the first linear layer. All right, makes sense. Run. Let's zoom out a little bit. Yeah, run this cell again. Yeah, and you can see I got a 2-dimensional tensor. That's what was needed for my linear layer. And that's the same principle that we followed in our previous example here in the official PyTorch tutorial, and this was just another example. And so this is very standard, very typical, very classical pattern you will see in almost all neural network involving PyTorch, because wherever you have a conv layer, and then at the end after the conv layer you want to do a linear layer fully connected once, and then you do this reshape. And to summarize at the end, so this is a rule for transitioning from a convolution layer output to a linear layer output. I must resize the convolution layer output, which is a 4-dimensional tensor, to a 2-dimensional tensor using view method. An example, a conv output of 32, 21, 50 by 50, that is batch number, channel, number of channels, height and width, should be flattened to become 32, then 21 into 50 into 50. That is, this is a two-dimensional tensor. Remember, don't get confused here. 21 into 50 into 50 is a single number. It's just a second dimension, but here they were separated by commas, so it is a four-dimensional tensor. So that means for the linear layer, the in features of the linear layer should be set to 21 multiplied by 50 multiplied by 50. Again, this is a single number, and this just denotes the second dimension. The first dimension continues to be the batch number. In this case, it's 32. And note another point, in these examples, I did not make use of nn.sequential module, because here the layers were built simply one after another, but in most cases you will be using nn.sequential, and in that case your conv2d and linear cannot be put in the same sequential section. Let's see an example to understand what I mean. So I am just going to my own GitHub, where a few days back I implemented the LeNet 5 architecture, which is exactly the same like this PyTorch tutorial. So this is actually LeNet 5, and I implemented it a few days back from scratch. So this is the code. It is the same structure. Input is 32 by 32, and then it goes through convolution, then fully connected layer. So let's see the architecture where I have it. Yes, so this is the code where the architecture is built from scratch. So this is what I mean. Say I have self.layer1 that has nn.sequential. It has conv2d, batch norm, ReLU, and max pool. Then another layer 2, which is again a conv2d, batch norm, ReLU, and max pool. Now within these nn.sequential, that is the same block of nn.sequential, I could not include my linear layer, and that's because the linear cannot be placed in the same sequential function right after the conv layer. The reason is that the input to linear needs to be reshaped, just like we discussed all this while. So you have to create two sections, one sequential for all your conv layer, and of course their associated pooling and activation layer, and then the output of these is reshaped to a flat tensor, and then this is passed to your linear layer. So this 400 is again calculated just like this, that my last conv layer will return me a 4D tensor, four-dimensional tensor, that needs to be reshaped into this two-dimensional tensor to be fed into my linear layer. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. In this quick video, I will do a visualization exercise of the 5 most popular activation functions with PyTorch, and those functions are ReLU, Tanh, Sigmoid, Soft+, and Leaky ReLU. So first, starting with the ReLU. So as the first step, I have to import all the relevant libraries, and then I want to create an input vector. So I'm going to use this torch.linspace, which will create a linear space, a linear vector, actually a linear tensor for me. This is taken from the documentation. It says create one-dimensional tensor of size steps whose values are evenly spaced from start to end. So my code for that will be, so to create an array in the linear space between -10 and +10, and let's say I want to have 2000 sample points. And this is that line, torch.linspace -10, that is the start value, then a stop value and 2000 sample points. Quickly check the shape. All right, and quickly check the shape. And I got a tensor of 2000 elements. It's a vector, that is, it's a one-dimensional tensor. Then for the plotting, I just want to convert these PyTorch tensor to a Numpy array. That's this, x equal to variable x, and then data.numpy. All right, I think just quickly check my Numpy. Yes, it is a Numpy Numpy format, and because it's a single dimensional tensor, so I got just 2000 as a first dimension and there is no second dimension. Now I want to define all my 5 activation function. So I already have imported the torch.nn.functional.f, and this functional module has all my activation function. I just have to pass them f.ReLU, f.Tanh, something like that. So let's do that. And with these 5 lines, I just created 5 activation function, and now I can just plot them one by one. So the first one, I'm going to plot my ReLU activation function, and as you all know, the value of ReLU ranges between 0 to infinity. It is mostly used between different hidden layers in a convolutional neural network. And to plot them, this is my code. Just I'm using the super simple plt.plot. To the x axis I'm passing x numpy, and for my vertical y axis I am passing this torch ReLU that has been defined here, and color is red, label ReLU. Let's run it, and I got my ReLU plotted beautifully. All right, now I'm going to do the next one, which is Sigmoid plot. Exactly the same code, and that's my Sigmoid plotting. Yeah, and then the next one, I'm going to do Tanh plotting. Again, the same code, only thing I have to change my y-axis value to Tanh, torch Tanh. That's my code. Run the cell, and that's my Tanh. And then I'm going to do soft plus. Now soft plus plotting, this is the function. This is taken from the documentation. Applies element wise function. Soft plus is a smooth approximation to the ReLU function and can be used to constrain the output of a machine to always be positive. For numerical stability, the implementation reverts to the linear function when input multiplied by beta is more than threshold. All right, let's just plot it because that's the purpose of this video. Same code, only difference here. Torch soft plus, run it, and I got my soft plus plotted, and by the looks of it we can clearly say it is just a smooth approximation. This part is a smooth approximation of my ReLU function. All right, next, leaky ReLU, the last one. So this again is taken from their documentation. Applies element wise function leaky ReLU. So in a standard neural network model, a dying gradient problem is common. To avoid this issue, leaky ReLU is applied. Leaky ReLU allows a small and non-zero gradient when the unit is not active. But dying gradient problem is not that common nowadays with the latest neural network architectures. All right, let's plot it. Same code, torch leaky ReLU, run it, and I got my leaky ReLU plotted. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn basic quantization technique in PyTorch, and the goal is faster model training and possibly better accuracy. First, let's just quickly understand why quantization is required at all. So, neural networks are implemented as computational graphs, and their computations often use 32-bit or in some cases 64-bit floating point numbers. However, we can enable our computations to use lower precision numbers and still achieve comparable results by applying quantization. So quantization refers to techniques for computing and accessing memory with lower precision data. These techniques can decrease model size, reduce memory bandwidth, and perform faster inference due to savings in memory and faster computing with int8 arithmetic. And now I will see an implementation in an actual code. So here I'm using PyTorch imports, all the regular ones, and then I will have a simple network build for my this network that you see currently. This is LeNet 5. So initially I have at the input end of the network a 32 by 32 size image, and then it goes through a convolution and subsampling layer, then another convolution, another subsampling, and then I have a fully connected layer. And finally, from the network, the final output is a vector of 10 different classes. So this network architecture is implemented for a multi-class classification problem, and here is the code for this network. So I have one conf, another conf, then one FC layer, FC2 layer, and FC3 layer. I mean, for the simplicity for this particular video, I have not included the max pooling layer or the subsampling layer over here because I have a separate detailed video on implementation of LeNet 5. Here the purpose is to see how my quantization is affecting my training time, my model size, etc. So first thing is, after I have this class defined, I just want to check what is the current value of the parameters here, whether they are float 32, 64, 16 or whatever. So for that I'm just printing my f32. Let's actually run this cell. All right, and now I'm just printing my model. All right, it just printed the various layers it has, and then let's see what's the by default what is these parameter it has taken. So for that I have to run this cell. What I'm doing in this cell, it's just I'm printing all the named parameters. So I'll be for n and p, and then I'll be printing the names and also the d type of p of the parameters. And from this I got the d type as float 32. So I can see that by default all computations and memory are implemented as float 32. And yeah, so now I am going to convert this default float 32 to float 16 with quantization. So basically I'm going to reduce a model to half precision in a single line of code. And the method I'm going to use is called half actually, and using half is often a quick and easy way to quantize your model. It's worth a try to see if the performance is adequate for your use case as a starter. So this is my code. Let's zoom in a little bit. Yeah, so I'm just taking FP32 model that was defined earlier and dot half. That's all you have to do. And now I'm printing again. And now I see all my parameters has been converted to float 16. And yeah, so that's sometime is the very first step. And I mean, in my cases, I pretty much keep my default parameters to F16, float 16, because it pretty much reduces my overall execution time by half and model size by half. So this was very simple and easy way to quantize my model, but in many cases, in most of the real cases indeed, you don't want every layer or every computation to be quantized in the same way. And also we may need to quantize beyond the float 16 type. We may need to go even further down. So for all those advanced cases, PyTorch provides 3 more methods to do that, which are dynamic quantization, post-training, static quantization, and quantization error training. Now, dynamic quantization is used when throughput is limited by compute or memory bandwidth for weights. This is often true for LSTM, RNN, or transformer network. And static quantization is used when throughput is limited by memory bandwidth for activation and often applies for convolution neural network. And the final one, the QAT, is used when accuracy requirements cannot be achieved by static quantization. And also a good point to remember here that a small portion of the network, in particular portions of the softmax operation, must remain in float 32. This is because the sum of a large number of small values, that is logits, can be a source of accumulated error. So better to keep the softmax operation at float 32. So now with these three, let's just see quick example of these three. So for dynamic quantization, I am going to use the same model that we had earlier, which is my model named fp32 underscore model. That's what we had from this LeNet 5 fp32 underscore model. And for dynamic quantization, all I have to do is this simple code: import torch.quantization, then quantized model will be torch.quantization.quantize dynamic, and then to that pass the first argument as a model, then specify the layers where you want to apply this dynamic quantization, and then dtype is where you define whatever the reduction in sizes you want in terms of the parameter number. So here I want int 8, so you have to mention torch.qint8, and then just run this. Let's run this cell and then also print the model, and then I'm printing the model. All right, so that's the same model. Now it is dynamically quantized, and let's check the linear layer if it is saying something. Yes, so my in features and out features, this is my linear layer, and dtype is torch.qint8. So this is an important thing to check after you do your dynamic quantization, that it really got implemented in your model layers. All right, now that was dynamic quantization. Now quickly compare my model size between fp32 and int8. And so for this, I just quickly wrote a quick function here to print the size of a model. So basically in this function, all I'm doing is I'm doing torch.save, and that is saving the model with its state dict, which will have all the model weights, parameters, and all related relevant stuff, and saving the model as temp.p, and then I'm getting the size of this temp.p by ways.path.getSize temp.p, simple, and finally I'm just removing the temp.p and return size. That's what I need, and I am going to invoke this function for both my fp32 model and quantized model, that is the one that we just did in the previous step, this one. So let's just run this cell. F stands for my original fp32 model, Q for the quantized model. Run this cell, and I got the model size as the 32 is 126 KB and this one is 70 KB. It's like what you are seeing right now, it's like 50% reduction. That's because this LeNet 5, the one that I built, it's super simple. There is no deep layer, and the input to the model is also super simple, a single tensor. But for any real model, you will see for when you are moving from fp32 to int8, what we did here, you will see almost a 75% reduction in your model size. All right, now that was quantization, dynamic quantization, and now we will see a quick example code of static quantization. First, I'm reading from the official documentation of post-training static quantization. So it says that post-training static quantization involves not just converting the weights from float to int as in dynamic quantization, but also performing the additional step of first feeding batches of data through the network and computing the resulting distributions of the different activations. Especially, this is done by inserting observer modules at different points that record these data. Let's quickly see a signature of these code for static quantization. And this is so our model was LeNet 5, so I'm just creating a variable here, static quant model, and then you have to bring in the qconfig of quantization. Here you will define that. So here I'm just using static quant model.qconfig equal to torch.quantization.getDefault qconfig and fbgem. I will come to the point of what this means in a second. First, just completely check what I'm doing next, and then I'm doing a preparation, that is what is done with torch.quantization.prepare, and then converting it with torch.quantization.convert static quant model in place true. So this line get default qconfig, and then I'm passing fbgem. What it does is it quantizes weights on a per channel basis and uses a histogram observer that collects a histogram of activations and then picks quantization parameters in an optimal manner. Now if you run this cell, let's see the output, then it will be a little bit more clear. All right, so this is my output, and what I have here is that it just printed all the layers and all the input shapes and things like that, the normal expectation. And then this is important, q scheme equal to torch.parchannel affine. This is for my fully connected layer 1. Similarly for fc2 and fc3, that is the next to fully connected layer as well, I have qs scheme equal to torch.parchannel affine and torch.parchannel affine. Now talking about these torch.parchannel affine, let's quickly see what PyTorch says about that. So I am in pytorch.org blog. So they say that there are two quantization scheme. One is PyTorch Tensor and then parchannel. So quantization parameters can be calculated for the layer's entire weight tensor as a whole or separately for each channel. So under so what we just saw, that is parchannel affine. So under these schemes, the separate clipping range is applied per channel, but under the per tensor scheme we can see the same clipping is applied for the entire tensor, and that's what it says, that in per tensor the same clipping range is applied to all channels in a layer, and but for the per channel it's separate. And then when we saw the definition of post-training static quantization in the official documentation, what it says is that this is done by inserting observer module at different points that record this data. Now in my code, back in my VS Code, where is that observer module? That is being taken care of by this line, torch.quantization.prepare. So this line will attach observers to the model. This will calibrate the training data. Calibration helps in computing the distribution of different activations. These distributions are then used to determine how activation should be quantized at inference time. But important thing to note here is this additional step allows us to pass quantized values between operations instead of converting these values to floats and then back to ints between every operation, resulting in a significant speed up. So basically this type of adding observer and the static quantization allows us to pass quantized values between operations without converting back and forth between floats and ints in memory, and which is what helps us to in a significant improvement in the speed up of my training. And then finally the third kind of quantization, which is QAT, quantization hour training. So under QAT, it typically results in the best accuracy. Float values are rounded to the int 8 equivalent, but the computations are still done in floating point. That is, weight adjustments are made hour that they will be quantized during training. And this is my simple implementation of a boilerplate kind of code for my QAT layer. So I am just making use of the same model, LeNet 5, then QAT model, then defining a qconfig with the same fbgemm, and then I am just passing these my original QAT model to torch.quantization.prepare QAT and QAT model, and let's run this cell. All right, so that was my QAT. And now I just want to show another example for the difference in model size between using quantization and not using quantization. But this time I'll be using a pre-trained model from Torch Vision, and the model I'll be using is MobileNet v2. And the code is this. So I'm just importing Torch Vision and then bringing in my model, MobileNet v2. So I have two model defined. One is with quantize equal to true, and another is I'm not passing these argument. That means quantization is false. And so the two models are model quant and model no quant. And now a very simple function just to do a torch.save of the state dict of the model, and the name will be demo.pt. And then I am just going to print these demo.pt size between these two models. Actually, I don't need this here. So then I'm just invoking this function to get the size of these two models. Let's see the size difference, if any. Yeah, you see, it's a really substantial size difference, because previously when I was checking the size difference with LeNet 5, I could not see such a substantial difference, because there my neural network was very simple, the depth was very low, and so that was the reason I did not see much of a substantial difference. The difference was, I think, 50% or so. But here I see such a huge difference. For quant model, I have only 3.63 MB of the model size, and it is 14.26 without the quantization. So that's the kind of benefit you get with quantization. And lastly, just create some quantized tensor to check that how they look like. So first I'm going to create a normal PyTorch tensor with this little code, t equal to torch.rand n, and let's print it. Yeah, so it's a vector, this list, which is my original tensor. And now first I'm going to convert this to a quantized per tensor. That's my code, torch.quantize per tensor. To it I pass this t, and we also have to mention the scale, the 0 point, and d type. And d type is the kind of d type I want. So here I want qint8 and run this cell. Alright, so that's my quantized tensor, and the d type is now torch.qint. Quantization scheme is torch.per tensor affine, because that's what we chose with this function, per tensor. And now I am also going to create a quantize per channel. For that, first I am going to create a new tensor. This will be a 3-dimensional tensor. Let's create a float tensor named torch.rand1 223. Print it. Float tensor. Yeah, so that's my 3-dimensional tensor. And now I have to define, before using torch.quantize per channel, I have to define scale, d-type, 0 point, and channel axis. And the difference this time is that for quantize per channel, my scale and my 0 point need to be a tensor. It cannot be a scalar like this. So let's just define those variable. All right, that's my scales. Scales is a torch.tensor, and just 1e minus 1, 1e minus 2, 1e minus 3. All right. D type is let's keep it at qint32. 0 point is again a tensor. Channel axis is 2, and now I can create quantized per channel. Alright, that's my code, torch.quantize per channel, and also print this variable q quantize per channel. Oops, what happened? Okay, I did not run this cell. Yep, so now it is converted to quantize per channel, and that's my resulting tensor. D type is torch.qint32, and the scheme now is torch.per channel affine. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this quick video, we will look at LeNet 5 architecture and how the input and output shapes of these various layers are calculated by following this classic formula of calculating the output shape of a CNN layer given the input shape. So first, this is the architecture at the top image here. So I'm starting with a 32 by 32 by 1 grayscale image. Then it goes through a 5 by 5 kernel, the first convolution layer, and outputs a 28 by 28 by 6 image, that is 6 here is a channel, and my output, the output width and height both are 28. Then I apply an average pool of stride equal to 2 and filter of size 2, and I get an output of 14 by 14 by 6. On these I apply the second conv 2, and the output of this conv 2 is 10 by 10 by 16. 16 is a channel here. And finally the average pool with stride equal to 2, filter size 2, and I get my matrix, the output matrix, 5 by 5 by 16. And this kind of the last matrix, because after these I get a fully connected layer which is a vector. So after this layer I get a vector with 120 elements that will be again changed to 84, and finally my Softmax layer, which will give me my final prediction, which is a 10 class representing the 10 labels of MNIST dataset. Yeah, so the entire thing is applied on the MNIST dataset, which has 10 classes and consists of only grayscale image. Now the in this video we'll understand these number, how they are getting converted from 32 by 32 to 28, then 14, then 10, and then finally 5, and then finally to a fully connected layer. So that's, to understand that, we have to apply this classic formula. It's a single, both I'm showing here two formulas. Actually it's the same formula, which is the top one for calculating the output shape of a convolution layer given the input shape. And it's super simple. You just do these addition and division. That is here n input is a number of input features, and in output is a number of output features. And when I say input features and output features, it could be either height or width. So if my n here is height, my output will be n height. That is, I will get the output shape of the height dimension. So anyway, so n is the number of input features. 2p, p is the padding size minus k, k is the filter size or the kernel size, s is stride, and to this whole expression you just add 1. So this is the normal convolution layer calculation. And for a pooling layer, because we have two average pooling layer here, for the pooling layer the same formula becomes just simplified to this, because for the pooling layer there is no padding. That means I only deduct my input features minus filter size divided by stride, and to this whole expression add the 1. So here I have taken example w here represent w width. So this is my input width, and after applying this formula I get my output width. Now let's apply this formula to understand our first layer, which the input to the first convolution layer is 32 by 32, and I apply a 5 by 5 filter with a stride of 1, and I should get a 28 by 28. Let's do my calculation. I'm just copying and pasting the relevant numbers here in this cell. All right, so that's my calculation. Input image is 32 by 32 by 1. Convolution, in the convolution layer I have k equal to 6, s equal to 1, p equal to 0, padding is 0, kernel size is 5 by 5, and k6 that is a number of channels. So that's just by the architecture of LeNet 5, that in after the convolution the depth is increased, so I get a higher number of channels. And let's just input these numbers into this formula here, and I get so the formula is this: input width minus kernel width plus 2 into padding, divide this whole expression by stride, and then this whole expression also need to be added with a plus 1. And if you do this calculation, 32 minus 5 plus 2 into 0 divide by 1 plus 1 gives you 28. And the same way, if you do this calculation for the height, that is input height minus kernel height plus 2 into padding, divide the whole thing by stride, and then to this whole calculation add 1, and that would give you 32 minus 5 plus 2 into 0 divide by 1 plus 1 is 22. So that's how we get these the output from the first conv layer as 22 by 6. and that's exactly what we just calculated here. And now you will see the second calculation here. Our second one is an average pooling, and now to the as an input to this average pooling, I will have 28 by 28 images, and the output from the average pooling is 14 by 14. Let's see. So my calculation is this cell here. So here my padding is 0, stride is 2, filter size is 2 by 2, and if I just include these numbers into my formula, input width minus filter width by stride plus 1, I get 14. Same for height. Input height minus filter height by stride plus 1 gives me 14. And again, I got these numbers 14 by 14 by 6. And 6, of course, is part of the architecture of LeNet 5. That's how my total number of channel, that is the depth of the network at this layer, is 6 I have kept. But we got the exact calculation of how 28 turned into 14 after the average pooling. All right, the next one is my second convolution, and here my input image out of size 14 by 14, that is coming from the previous pooling layer. So let's do the calculation here again. So I'm just pasting the calculation in this cell, and this is a calculation. So input width here is 14, and input height is also 14. Stride remains 1, padding is 0, and kernel size is 5 by 5. Just include this number, I get 10 as the output of this formula, and for output height as well I get 10. And that's exactly what we have here at the conv2 output. The conv2 output is 10 by 10 by 16, and 16 is again the number of channels, which is part of the architecture. And the next one is the second pooling layer, and by looking at the architecture, I can see here the input will be 10 by 10, filter size is 2 by 2, stride is 2. So let's put the calculation here. All right, input height is 10, input width and input height both are 10, and my filter width is 2 because filter size is 2 by 2. So just including the and padding is 0, stride is 2 again. So just input this number to my formula, and I get the output from this second pooling layer as 5 for width and 5 for height as well. And that's exactly matches with the architecture image here, 5 by 5 by 16 after applying the average pooling. And then the first fully connected layer, there I have I need to get practically 1 by 1 by 120, because here it's a fully connected layer, and which is a vector of size 120. So I should get a width of 1, height of 1, and only then this one matches. That is, this vector actually represent 1 multiplied by 1 multiplied by 120. So let's just do the calculation. And here's my calculation. Here my input width and height is 5, coming from the previous layer. Stride is 1, padding is 0, and kernel size is 5 by 5. So just include this number to get the output width. So 5 is input width minus filter width is 5, that is a kernel size, divide by 1 and multiply add the whole thing by 1, and you get 1. Exactly same calculation for height. 5 minus 5 by 1 whole plus 1 gives you 1. All right, so now and the output depth is 120. So the output vector matches exactly what I was saying. The output vector is output width multiplied by output height multiplied by output depth, that is 1 into 1 into 120, and that's exactly what we have in this fully connected layer. So that was so that's how the calculation is made. LeNet 5 is a classical and super simple neural network architecture, but this formula in this way you can apply to any neural network architecture that you are doing to make sense of these size numbers. And now I am going to implement the same architecture in PyTorch, and I will not go too much in detail into the every step, because just few days back I made a separate video on LeNet 5 architecture from scratch. Here is that video. I will put a link in the description of this video. Here I went in detail of step by step every line pretty much, that to implement this LeNet architecture from scratch with PyTorch. So what I'm going to do, I'm going to take the same code here that I built in that video, and see that it's working, that and all this calculation that we just did here, that actually matches with the output of PyTorch layers. So let's first import all the relevant libraries, which are these. Only the regular one, torch and torch.nn conf2d. Only extra thing is that I want to import this extra library called torch summary. This line from torch summary, import summary, so that I can print all the layers in a beautiful way. So the code for the architecture is just this. Let me copy it from my other file. Yeah, here it is. So this is the code for implementing the same architecture. So overall we have two conv layer, two subsampling layer, which is my max pool 2D layer here. That is, I'm not using the average pool, I'm using max pool, just because kind of max pool is currently the most popular one. Average pooling is slightly falling out of the popularity contest. And I also have three fully connected layer. The first one is here, FC, the second one is FC1 and FC2. So just look at the original architecture here again. I'm starting with 32 by 32 by 1. First conv layer, which is outputting 28 by 28 by 6. Then an average pool. In this case, for my code, I'm using max pool. From there, I'm getting a 14 by 14 by 6. Then I am applying the second conv. Then another average pool or max pool in my case. And then after this, I'm getting my first fully connected, then another fully connected, and then finally the output from the neural network. And this is our code. So my self.layer1 is includes my conv 2D and my max pool 2D. And of course, I have included my batch norm and ReLU inside these layer 1. Then layer 2, I have conv 2D, max pool 2D, and again batch norm or ReLU are included in this. And then after these layer 1, layer 2, I have my fully connected, then another ReLU, then next fully connected, then another ReLU, and finally these FC2, which is the last fully connected one. And then my forward function, this will just implement these same architecture layer by layer. That is, the output from the previous layer will be the input to my next layer. All right. Now let's run this, and I am going to take a dummy tensor to check that this is working. Let's go my next cell. All right, so what I'm doing is I'm just creating another the object from this class and passing it the number of classes as 10, because this LeNet 5 was specifically designed for MNIST dataset, which is of 10 classes. And that's why I'm passing 10. And to the input size, I'm just passing 1 by 32 by 32, because that's how it expects the input to be. Remember the input image at the very first stage to the entire network, I have to pass a 32 by 32 by 1. 1 is a number of channel because it's grayscale. So this is what I'm doing in my summary function, and summary function is just what we discussed, that this is from this package torch summary. So input layer is a tensor, which is 1 by 32 by 32, and device I'm mentioning CPU, and that's just because that is kind of required for the summary package to run properly in the local machine. I could not run it with GPU. All right, that's a separate thing. So just mention your device to be CPU if you are running summary in local machine to get the correct output. All right, now just run this cell. And beautiful, I got the entire output very well presented here. So let's understand. So my first conv to the output is 28 by 28 by 6, exactly what matched with this one. Let's put this image into that cell down below so that we don't have to go back and forth again and again. Let's just put a markdown here, and yeah, perfect. Now what I'm seeing is, so this 28 by 28 matches with here after the first conv layer. Then I am getting another same dimension, that is 6 by 28 by 28. That because I have a batch norm 2D and ReLU before my first max pool 2D. So they are batch norm 2D and ReLU. They will not change the dimensions, and that's why I'm getting the same dimension here as well. Then my max pool 2D, and from there I'm getting 14 by 14, exactly what is required here and what we saw by our manual calculation. And then the next conv 2D, from there I'm getting 10 by 10. Here also in the image it's 10 by 10. And then batch norm 2D and ReLU again, which will not change the dimension because in the layer 2 as well, I have my batch norm and ReLU inside this layer 2. All right. And then after my second ReLU, okay, this is the second subsampling, that is the second max pool 2D. Here I should get 16 by 5 by 5, and that's exactly what the architecture as well, 5 by 5 by 16. And then after that is a fully connected layer. So fully connected layer, I'm getting -1 and 120. -1 just represent that this dimension is to be inferred, and here in the PyTorch case of PyTorch, for all these cases, the first dimension is the number of samples in a batch, that is a batch size. So anyway, linear one is 120, what we see in the image as well, it's 120, and that's what we also got by our calculation. Remember, when we calculated the first fully connected layer, we got 120. And after the first fully connected layer, I got after 120, then next is 84, and that's what we are getting here. And I have a ReLU after this, so that's why I am getting another 84 here. That will not change the dimension. And finally, from the output of the entire network, this is the 10 classes, and that's what I get here, that it's a vector of 10 elements representing 10 separate classes of MNIST dataset. And total number of parameters, trainable parameters, are 61750. And yeah, so we saw that the entire calculation of this LeNet 5, all these sizes calculated manually, exactly matched after we implemented this with PyTorch. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one. In this quick video, we will visualize some of the common learning rate scheduler from PyTorch's Optim module, and then build a custom learning rate scheduler taken from the CycleGAN paper. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So learning rate is an important hyperparameter in gradient descent. Its value determines how fast the neural network would converge to a minima. If the learning rate is too slow for the neural network, the process of convergence would be very slow, and if it is too high, the convergence would be fast, and there is a chance that the loss might overshoot. And that's why the concept of adjusting the learning rate comes into the scene. Instead of taking a constant learning rate, we can start with a higher value of learning rate and then keep decreasing its value periodically after certain iterations. This way we can initially have faster convergence whilst reducing the chances of overshooting the loss. In order to implement this, we can use various scheduler in the Optim module of PyTorch. So first, I will make use of some of the inbuilt learning rate scheduler in PyTorch, and for most cases that will be sufficient for your requirement. And then I will build the custom learning rate. So initially I'm just importing in this cell all the regular imports, and also I'm importing this AlexNet pre-trained model from Torch Vision, because I will be running my learning rate schedule on this neural network of AlexNet. Then in the next cell, I'm just building this model of AlexNet. It's absolutely simple one. To the AlexNet, I'm just passing a num class is equal to 2, and then using an optimizer. My optimizer in this case is defined to be SGD, stochastic gradient descent. And to that, I'm passing the initial, that is a base starting learning rate of 0.001. And parameters remain model.parameters, which will be derived, which will be extracted from this model. And first I will be using this multi-step LR learning rate scheduler, and just as the name says, it reduces the learning rate on a step-by-step basis, and the steps that I am supposed to mention as a hyperparameter in my code. And these are the parameters that multi-step LR takes. Optimizer obviously is the wrapped optimizer. It can be SGD, Atom, etc. Milestone, this is important. So this is a list of epoch indices must be increasing. That means these are the milestone indices where, or milestone indices of your epochs where the learning rate scheduling will be taken effect. That is, at those steps or those milestones, the reduction of learning rate will be applied. Gamma is a multiplicative factor of learning rate decay. And then let's just get the code. All right, this is my code for multi-step LR. I'm just defining a variable scheduler with LR scheduler.multistep LR, and then giving as an argument optimizer that has been defined at the top. Milestone I'm keeping at 30, 60, 80. So these are the epoch numbers where my learning rate will be decreased. And gamma equal to 0.5. That is again a multiplicative factor for my learning rate decay. And then I'm just declaring x and y variable to be plotted horizontally and vertically respectively, and running this loop of 100, and these are my epochs. And inside my epoch, I am first doing optimizer.step, which will update the parameters based on parameters.grad. And then next line is scheduler.step. Now note here, because you keep your step of the scheduler after your epoch, that means the first epoch will have your initial value of the learning rate, which in my case is 0.0001, and if you run for multiple epochs, then it will continue to be decayed. That is, scheduler.step will update your learning rate. That is, this has the job of decaying your learning rate at these milestones. And this LR variable will just get the actual learning rate by running this little thing, scheduler.getLR. This method will actually extract the learning rate from the scheduler. And finally, when you get the learning rate, you just append it to y variable, and then I'm plotting both x and y. Let's run this code. And the output I got is this plot. So we can see here that at these milestones, that is, my milestones are 30, 60, and 80. And looking at the plot, we can see at 30, 60, and 80, the learning rate actually dropped. And that's how it works, that it will stepwise basis, it will reduce or decay your learning rate. All right, now the next one is lambda LR from the Optim module of PyTorch. So here I am in the official documentation of PyTorch for lambda LR, and what it says about this function is that it sets the learning rate of each parameter group to the initial learning rate times a given function. So that's the most important part, initial learning rate times a given function. And these given function, that part is controlled or configured through this argument called LR underscore lambda. And this LR underscore lambda is a function which computes a multiplicative factor given an integer parameter epoch or a list of such functions, or one for each group in optimizer.param groups. So let's see the implementation, then it will become clear. So basically my new learning rate will be followed by this formula. That is, my new learning rate will be the initial or the base learning rate multiplied by a multiplicative factor which may come from a separate lambda function. So this is my implementation, a very simple one. So in the first line, I'm just defining a lambda function, and this is very simple: 0.95 exponentiation epoch, and the epoch will be decided when I will run the epoch loops. And also my scheduler, this variable is just an object created from torch.optim.lrscheduler.lambda lr, and which takes my optimizer as the first argument, and this lr lambda argument is output from my lambda function. And then to plot it, just as the previous one, I am defining an x variable from the range of 100, and then I'm running this epoch from 0 to 100. And again, the regular step, optimizer.step to update all the parameters, then scheduler.step, and then my learning rate I get by extract by this function get lr on my scheduler. Finally, while running this loop, I'm appending each of this learning rate to my y variable, and then finally I just plot it both x and y. Now let's just run this cell and see the result. All right, so that's my plot. On the horizontal axis, I have all the x variable up to 100, and this is my learning rate. As we can see that with the epochs, it continues to decay gradually. And the next one I'm going to check out is called exponential LR. And again, the documentation says that it decays the learning rate of each parameter group by gamma every epoch. And so the parameters it takes is obviously the first one is optimizer, then gamma, which is a multiplicative factor of learning rate decay, last epoch, and verbose. All right, let's go to my VS Code and let's run it. This is my code, again exactly following the similar structure. Only difference here is that I am defining this hyperparameter called gamma, which is a multiplicative factor, and then I'm just regularly plotting it. Let's run this code. All right, so this is a plot of the various learning rate for various epochs. And then another one I'm going to check for learning rate is cosine annealing error. And here I am in the documentation of this function, and it says it sets the learning rate of each parameter group using a cosine annealing schedule, where eta max is set to the initial error and t current is the number of epochs since the last restart in SGDR. So this learning rate was proposed in a research paper, and basically this variation of learning rate happens according to the cosine annealing schedule. Mathematically, if the learning rate is given as this equation or this expression, then cosine annealing learning rate is what is applicable. And this equation was proposed in the paper, and here eta t is a current learning rate. Eta max and eta mean are the maximum and the minimum learning rates respectively. T current is the current number of accumulated epochs. From the above equation, we can see that once T current equal to T max, the learning rate becomes eta mean. So cosine annealing learning rate is a scheduling technique that starts off with a very large learning rate and then aggressively decreases it to a value near 0 before again increasing the learning rate. And we will see that with an actual code. So let's do that. And this is my little simple code to implement this learning rate and also to plot it with 100 epochs. So let's run this, and before that, the main parameters that I'm passing to this cosine annealing learning rate is T max equal to 20 and eta mean equal to these 0.00001, and here this eta mean is the minimum achievable learning rate with the given cosine annealing schedule. So let's just run this cell. All right, this is the expected behavior of cosine annealing learning rate. Here we start off with the learning rate, then it reduces aggressively, goes very near to 0, and then again goes up aggressively, and this cycle goes on. And the next variant of cosine annealing error is cosine annealing worm restarts. Quickly check out the documentation. Here it is. Sets the learning rate of each parameter group using a cosine annealing schedule, and the arguments are almost like the same what we used for cosine annealing error only. Let's quickly implement that in code. So the code is this, and just the same structure I'm using here, and let's run this cell. All right, this is the plot I got for cosine annealing worm restarts. So you can see the plotting are kind of similar what we plotted for cosine annealing error only. So for the restarts one, that is this one, this learning schedule, the key concept here is that in order to find a more stable local minimum, we can increase the learning rate from time to time, encouraging the model to jump from one local minimum to another if it is in a steep throw. And this is called the restarts in stochastic gradient descent with restarts. So the whole concept is called SGDR, and this is that restarts, that the learning rate falls steeply and then suddenly jumps to a very high value, then again falls steeply, suddenly jumps to a high value. And in this way, the strategy is that we find a more stable local minimum with this technique. And the next one in our list is this one, cyclic LR. And the documentation says that sets the learning rate of each parameter group according to cyclical learning rate policy, CLR. The policy cycles the learning rate between two boundaries with a constant frequency, as detailed in the paper Cyclical Learning Rates for Training Neural Networks. The distance between the two boundaries can be scaled on a per iteration or per cycle basis. And cyclical learning rate policy changes the learning rate after every batch. Step should be called after a batch has been used for training. All right, now let's go back to our code to see the actual code. And this is the code. Again, the similar structure. I'm using cyclic LR from LR scheduler, and optimizer base LR 0.05, max LR 0.1, step size 10, step size down 20. Step size up 10 and step size down 20. All right, then I'm plotting for 100 epoch. Let's run this cell. All right, this is the plot and this is the cycle we are talking about. And the next one is one cycle LR. This sets the learning rate of each parameter group according to one cycle learning rate policy. The one cycle policy annuals the learning rate from an initial learning rate to some maximum learning rate, and then from that maximum learning rate to some minimum learning rate much lower than the initial learning rate. Okay, so you have to remember this point when setting the hyperparameter. The minimum learning rate should be much lower than the initial learning rate. This policy was initially described in the paper Superconvergence, Very Fast Training of Neural Networks Using Large Learning Rates. The one cycle rate policy changes the learning rate after every batch. A step should be called after a batch has been used for training. Let's see the code. So that's my one cycle LR and that's my code. So I'm setting the max LR 0.1, step per epoch is 10, and epoch totally and epochs are 10. So let's run it. All right, so that's my cycle, and we can see that this minimum here is relatively much lower than the initial learning rate. All right, so these were some of the common and inbuilt learning rate scheduling technique from within PyTorch, but now we are going to see a custom learning rate, and for that I'm going to refer to a paper, a very popular paper called CycleGAN, and the official name of the paper is this: Unpaired Image to Image Translation Using Cycle Consistent Adversarial Networks. And in this paper they proposed a particular way to calculate the learning rate because that was their strategy. And while implementing paper, almost all paper have their own strategies or own recommendation for implementing the learning rate, and so most of the time while implementing a paper from scratch or while trying a new algorithm, you do have to fall back on creating a custom learning rate scheduling technique, and that's why it's so important to learn this. So let's first see what this paper talks about about their way of calculating the learning rate scheduling. And they say that we keep the same learning rate for the first 100 epochs and linearly decay the rate to 0 over the next 100 epochs. So the total training will run for 200 epochs, and the first 100 epochs the learning rate will remain same at the base rate or the initial rate, and after from 101 to 200 I have to linearly reduce the learning rate, so that by the end of the training, that is end of the 200 epochs, it becomes 0. And to implement this, the first thing I will do is to use this very popular module of PyTorch for scheduling the learning rate, that is torch.optim.lrscheduler.lambda-r. And the thing to understand here is that this lambda-r function takes an argument called lr lambda that sets the learning rate of each parameter group to the initial learning rate times a given function. That means when I implement this function, each new learning rate will be equal to the old, that is a base learning rate or the initial learning rate multiplied by lambda epoch. And this lambda can be a function or can be an integer, a value to multiply this initial learning rate with. So this is the most fundamental thing to understand. And then let's go back to my utils function to check my implementation. So this is where I'm implementing this concept. It's a very simple method. Let's understand this. And this class basically just returns the original base learning rate if my current epoch is less than 100, and 100 means this one, decay start epoch, this argument. And in this case of the CycleGAN, decay start epoch is 100, very clearly written in the paper. So if the current epoch is less than 100, then just return the original learning rate, that is a base learning rate. And if it is more than the decay, then do this calculation here, that is this line. Just return this line, and how this line is working we will see in a second. But first, in the assert statement of the class, I'm just checking that total number of epoch is minus decay start epoch is greater than 0. That is basically total number of epoch should be more than 100. Only then this whole thing will be applicable, otherwise it will give assertion error. And all right, so now checking for these below line checks whether the current epoch has exceeded the decay epoch. I have put some comments here to make it clear. For example, if the current epoch is 80, then see what happens. Then max 0, current epoch is 80, it will be 80, and self.offset in this case will be was 0. We'll see that when implementing in the train.py. And minus self.decay start epoch. So for the epoch of 80, I will get this value within the max function. So max 0, 80 minus 10, 80 minus 100, that is 0, max 0 minus 20, which will return me 0. That means in this entire expression, that is a whole return statement, this numerator part will become 0 in that case. So 0 by something will return me 0. So the step function will return me 1, and that will be the return value from this lambda function. And actually this return value is the multiplicative factor which will be multiplied with my base learning rate, what we saw in this formula here. So the way that these learning rate scheduler of PyTorch will work is that this base learning rate will be multiplied by the multiplicative factor coming out of the lambda function, and that will be my new learning rate. And when it is 1, my original learning rate continues, and that's a case for any value of epoch which is less than 100. Now see what I will get for any value which is more than 100. And now let's say my epoch is 110, which is more than 100. Then see what these lambda function will return. So I have just put these return statement here, and in this case for epoch equal to 100, this will be the calculation 1 minus max 0, 110 plus 0. This offset is remaining 0. We will see that in implementation. Minus self.decay start epoch, which is 100, divide this whole numerator by self.number of epochs, which is 200. In this case, in the case of CycleGAN, we will be running up to 200 minus self.decay start epoch again, which is 100, and this will return me 1 minus max 0 to 10, which will return me 10. That is, this expression will become 10 by 100, that is 1/10. So the final output from this calculation will be 0.9. So in the case of epoch equal to 110, my multiplicative factor is 0.9. That means here in this expression, the new learning rate will be decayed or reduced by these factor. That is, the new learning rate will be the base learning rate multiplied by 0.9. And that's how this decay factor will work with learning rate scheduler. Now let's see another example. Say my epoch is 120. In this case, doing the same calculation, I will get the multiplicative factor as 0.8. So my new learning rate will be the initial learning rate multiplied by 0.8. Again, it is decaying, and remember, this initial learning rate is the original base learning rate that we defined at the very start of the training. It is not getting updated. It is not the immediately preceding learning rate. So this learning rate is original base. So that means if I continue reducing this way, then there will come an epoch where my learning rate becomes 0 actually. And that's the purpose of this calculation here. That is, this lambda LR function. That is, by the end of 200 epochs, I need to make the learning rate to 0 by continuously decaying from 100 to 200. So to summarize in this line, what we are doing is we are dividing the learning rate equally for the last 100 epoch and keep reducing the base learning rate from 101 epoch up to 200 epoch. And in doing that, because we are dividing the last 100 equally, by the end of 200, the reduction of learning rate will be so much that it will come to the value of 0. And finally, for the actual usage of this lambda LR class in my training, let's go to my train.py file. So again, this lambda LR class was defined in my utils.py file, where I had few other methods defined as well, which are all utilities method. And then the train.py file is where I was running my entire CycleGAN architecture, and that is a long file which has many other implementation of the full architecture. But what is needed for this video is the implementation of these custom lambda LR to be included into my learning rate scheduler variable. That is, learning rate scheduler will make use of torch.optim.lr scheduler.lambda-r, which we discussed earlier in this video. So this function, again, just to recap, this module, lambda LR module of PyTorch, takes argument which will called LR lambda. So this is part of the official argument of lambda LR, and this LR lambda practically is a multiplicative factor, and that multiplicative factor is coming from this custom lambda LR. So if you look at the code again, so this is my learning rate scheduler underscore g. This is a variable, and then within the lambda LR function, I am passing this LR lambda argument, and that is equal to the output of my lambda LR dot step. So basically, this lambda LR is decaying my learning rate by its output. And in this architecture implementation of CycleGAN, I have 3 learning scheduler. As we can see, LR scheduler underscore G, LR scheduler underscore disk underscore A, and LR scheduler underscore disk underscore B. And all of them are using the same structure. That is, the LR lambda is implementing my custom lambda LR class. And as a separate point, just in case if you're interested, that this train.py file and the utils.py file is part of my entire CycleGAN architecture implementation from scratch with PyTorch, for which I have a separate video, and I will give the link of that video in the description of this one. So just in case if you're interested for that, where this whole custom learning rate was implemented and the entire architecture of CycleGAN was built from scratch. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will implement Hausdorff distance, a very important metric in semantic segmentation and object detection. So here I'm looking at the Wikipedia page for Hausdorff distance, and it says this the Hausdorff distance is the longest distance you can be forced to travel by an adversary who chooses a point in one of the two sets, from where you then must travel to the other set. In other words, it is the greatest of all the distances from a point in one set to the closest point in the other set. So that was one definition of Hausdorff, and another way these distance can be expressed is the line right here, that it measures how far two subsets of a metric space are from each other. So basically the Hausdorff distance is the maximum of all the minimum distance between two curves. Let's see what I mean. So I have here, for example, two curves, and the red one and the blue one, and first I need to calculate the minimum distance between the closest point between these two curves, and then I take the maximum of all the minimum distance between these two curves. That's Hausdorff distance. So it's this Hausdorff distance is the greatest of all the distances from a point in one set to the closest point in the other set. So for an intuitive understanding why we need this Hausdorff distance at all, I found this beautiful blog right here. The link is cgm.cs.mcgil.ca. I'll probably give this link in the description. So what they are basically saying is that, let's quickly go through the blog. One second. Yeah. So the definition of distance between polygons can become quite unsatisfactory for some applications. Let's see an example, figure 1. So take a note of this figure right here, two triangles. The shortest distance here, the problem here is that shortened distance does not consider the whole shape. And why is that so? Let's quickly read through this block. We could say that the triangles are close to each other considering their shortest distance, which is this distance shown by the red vertices. However, we would naturally expect that a small distance between these polygons means that no point of one polygon is far from the other polygon. In this sense, the two polygons shown in this figure are not so close really, as their farthest point shown in blue, that is this point and this point, could actually be very, very far away from the other polygon. Clearly the shortest distance is totally independent of each polygonal shape. So that's one problem with calculating the shortest distance between two shapes. Let's take another example, this one, another example given in this figure 2, and here the problem is the shortest distance doesn't account for the position of the object. So what they're saying is, where in this figure we have same two triangles at the same shortest distance than in figure 1, but in different position. It's quite obvious that the shortest distance concept carries very low informative content, as the distance value did not change from the previous case, while something did change with the objects, that is their position indeed. So these are the problem with calculating the shortest distance between two shapes. So, and this problem is more or less solved by the special distance called Hausdorff distance, which is the greatest of all the distances from a point in one set to the closest point in the other set. And the blog also gives a little pseudocode. You can go through this pseudocode to get the understanding of Hausdorff distance. All right, so that was some theory behind Hausdorff, but now I'm going to implement it, rather use some packages to actually find Hausdorff distance between multiple tensors. And so PyTorch or TensorFlow doesn't have Hausdorff right inside it built in, but there are quite a few packages, and one of the very popular one is this one right here that I'm looking at, called Hausdorff. And yeah, so they have 182 stars, and last updated in 11 months ago. So yeah, this is one of the popular ones. So I am going to take few examples from these GitHub repo itself. They have given a couple of examples to implement it. I'm just going to follow that directly. So the first you have to, of course, install this package by doing pip install Hausdorff, and then let's do some coding here. SNP. I also need that. I have already installed that in my machine. From Hausdorff, import Hausdorff. All right, and now I just need to create two arrays from following the repos example, which is this. So I'm just creating first with a np.random.seed0, and then x and y are my two tensors of this shape, that is 1000 by 100. The column must match between them. That is, the second dimension must match between them. Let's run it. Yeah, obviously I got 1000 by 100 and 5000 by 100. And now I am going to print few things, again following their repo as it is. So here, test computation of Hausdorff distance with different base distances. So for the distance in this package, for this distance argument, you can give different distances: Manhattan, Euclidean, Chebyshev, and cosine. And also we can give custom distances according to your requirement. We will see the example right now, but first let's run this cell. Wow, they just calculated the Hausdorff distance for x and y, and keeping all these different distances. So the first one is Manhattan distance, Hausdorff, and the second one is based off Euclidean, third one is Chebyshev, and the fourth one is cosine. And now I am going to do a custom implementation of Hausdorff, and again following their repos instruction exactly. So that's my custom implementation. First, oops, sorry, this is not a custom distance, because this is still using the predefined Haber-Shine distance. So let's just delete it. Instead, my custom distance will be this one. So here I am first I'm importing number, because this is just-in-time compiler for Python that works based on code that uses NumPy arrays and functions and loops. And the most common way to use number is through its collection of decorators that can be applied to your function to instruct number to compile them. So this at number.jit, this is the most common way of using decorators with number. And then I'm defining a custom distance function. It's pretty much an Euclidean function. So this is I have two array x, array y, and then what I'm doing is for I in range n, and n is my the shape 0, and for I in range a, I'm just calculating the Euclidean distance by squaring array xi minus array yi, and returning this whole expression square root. All right, and now to use my Hausdorff distance, all I have to do is, one second, all I have to do is include this another print statement here where I am using the distance, these custom distance method. And then obviously I'm passing x and y that has already been defined at the top. That is this one. So let's run this. Awesome. So that's my custom distance functions implementation of Hausdorff. Now we can do many more crazy custom function implementation. Their official repos suggest another one, which is this. So here again, my custom distance function is much more kind of crazy. So what I'm doing is array xi minus array yi, taking cube of that, dividing this whole expression again by array xi square plus array y I square plus 0.1. It's pretty kind of very unique one for calculating the distance between array x and array y. And then again, I'm just bringing in Hausdorff distance, and to the distance argument I'm passing these custom distance method. Let's run it. Yep, I got my Hausdorff custom crazy test output as this. So those were implementation with that package. That is this one, Hausdorff. But now I'm going to calculate Hausdorff using SciPy and Mon-I. You must be knowing both of them. It's two of the most popular packages in this world of machine learning and data science. So let's bring in some the standard modules from SciPy and Mon-I. So from SciPy.spa spatial, I need to bring in okay, I need to do distance here and import directed. That was Hausdorff, yeah. And I also need to do the same need to bring in Hausdorff from Mon-I. I really just suggest you go through their documentation, because their documentation really explains well. I have to bring in Mon-I.metric, metrics.utils, and from there import get mask ages, this one, and also get surface, I think this one, get surface mask, no, get surface distance it should be, FSCE, DIS, yep, this one. So with these two modules or these two methods of Mon-I, I will calculate the Hausdorff distance. So first let's do it for the SciPy one. Calculate. It's a difficult word to spell. Hausdorff, D-O-R-F-F. Yep. And I need to pass in two tensor to it. My two tensors would be my prediction tensor, that is a predicted output values from my model, and the ground truth. So let's give pred gt and then max distance. And if np.all, obviously if all pred are equal to gt, the ground truth, then I just need to return the distance as 0, because in that case there is no distance between them. They are just, in a perfect world, predictions will be the same as ground truth. Return 0.0. I have to return float. That's what I'm doing, 0.0. And otherwise calculate the distance between them, which will be my directed Hausdorff and To that, I will pass my np dot. I need to bring in all the I need to find the indices of the array elements that are non-zero. So I'm going to do arg_where here. To that, I will press spread. Similarly, np.arg_where gt, and I don't need max distance yet here. Rather, I need to get the 0th element from this here. So distance will be directed Hausdorff np.arg_where prediction. Okay. And if dist greater than max dist, then so when gt ground truth are all 0, this may get to infinity. So if dist, sorry, it will be dist max distance, then it will be return 1.0, and otherwise return dist by max dist. And if you are thinking that why I had to bring in this 0, that is why I had to take the 0th element from the output of directed Hausdorff, it's pretty much as following their documentation. So this is official documentation of the directed Hausdorff in scipy.spatial, and this actually computes the directed Hausdorff distance between two 2D arrays. And what they are doing is similar, that is they have two tensor u and v, and they are calculating the directed Hausdorff on them and taking the 0th element from them. And that's because in the return value, that is what this method returns are these things. That is, the first one is it's a double value, which is a directed Hausdorff distance between array u and v. Then it returns the second thing, which is index of point contributing to Hausdorff pair in u, and then third one is index of point contributing to Hausdorff pair in v. So you obviously, when you want the actual scalar value of the Hausdorff distance, then you obviously need to take the first element from the return array. And this max distance argument is something that we have to separately provide. So now I'm going to do the same calculation of Hausdorff based from the package Mean-IoU. So let's define another function. Let me position it. Calculate Hausdorff, which is DOR. Actually, this one should be named as SciPy. SCIPY. Yep. It's a US DOR under MON-AI. And this also take red and GT and max DIST. So here, if np dot all pred equal to GT, then return 0.0, else. Now here is where I need I have to implement this method that we brought in from the Mean-IoU package, which is get surface distance. To that I will pass first I want to make use of get mask edges, and that to that I'll pass spread and GT. And actually, if you go to the official documentation of Mean-IoU and read their get mask edges, this is what they mention. This method do binary erosion and use XOR for input to get the edges. This function is helpful to further calculate metrics such as average surface distance and Hausdorff distance. the input image can be binary or labelified images. All right. So yeah. So from the get mask edges, I first get the what do I get? I first get the ages predicted and ages ground truth. That's what the get mask edges returns me. Uh, Return type tuple ND array both are will be ND array. All right. So let's get back to our VS Code. Yeah, get mask ages. To that I pass GTN. Okay, and this will return me a tuple. So they will be my ages spread and ages GT. Oops, sorry. Ages GT. All right. And now, why? Yep. And now I have to make use of these two return values and apply them on get surface distance to get my surface distance. So surface, yeah, it's distance. Oops, why? Yes, ISTA. Surface distance equal to get surface distance. To that I pass ages spread and ages GT, and also the most importantly the distance metric. And once again it can take various distance metric, and in this case I'm going to pass Euclidean. What are the documentation saying? That we can pass Euclidean, chessboard, taxi cab. Yeah, so I'm going to take Euclidean one. CLIDEAN. All right, and now if surface distance is equal to 0 comma, then I'm going to return 0, else I have to calculate the distance as. So this distance is pretty much my Hausdorff distance. That will be equal to surface distance. I have to take the max, of this. And then just like this function, I'm going to do this little thing as my final return value. If the distance distance greater than max distance, then return 1.0, else return, oops, I'm always misspelling, return distance divided by max distance. Okay, now I'm going to create a random tensor shape which I'm defining to be 128 by 128, and also I'm going to define my max distance by giving a custom function. So my custom definition of max distance will be equal to np dot square root, and to that I'll pass random tensor shape, take the 0th element, and then just cube it to the power of 3. To that I will add random tensor shape 1 and cube it as well. Am I doing it right? There is something, yep, this will come inside this. Yeah, so np dot square root random tensor shape 0 to the power cube plus random tensor shape 1 to the power of 3, and taking this whole expression, it is being square rooted by np dot square root. And now my thread will be np dot random np dot random random dot rand int, and to that I will pass the starting position remains 0, and for the high I will pass gh equal to 2. Size will need to match my random tensor, random tensor shape, and similarly I need to do for another vector which will be my ground truth vector. So just I'm copying it down below and naming it gt vector. Otherwise it remains same, np.random.randint 0, high equal to 2, size sham. Yep. Just print their shape to check that they are what they should be. Print actually I can print let me see 1 second. GT vector. Okay, just do it. GT vector.shape. Yeah, obviously. Okay, so now I can, and let me just print my final calculation. That is the final Hausdorff distance calculated from those two functions that we defined. So first one is Hausdorff SciPy. Oops, I'm again pressing enter, which is, I should press just tab. Calculate Hausdorff SciPy. To that I pass my pred vector and also my ground truth gt vector and max distance. Similarly I do print calculate calculate, why that's not coming, calculate Mon-AI. Oops, sorry, HAUS Mon-AI. To that I pass pred, then gt vector and max distance. And now if I print, that should give me name Hausdorff SciPy is not defined. So what did I define? Oh, I never ran this cell. Yep. The truth value of an array with more than one element is ambiguous. So let me debug this. The error is coming from here. If surface distance equal to 0. Oh, so I think I got it, because I'm comparing a whole tensor with just a tuple. So it must be some form of shape. Let me see. This is the line, if surface distance, yeah, obviously. So I did not ever take the shape. I cannot compare. So the surface distance will be a whole tensor. I cannot compare that with only a tuple. I need to get the shape. This HAPE. And then it should be all right. So let me run it again from here. All the code cells below. Yep. So now it ran well, and I got the Hausdorff SciPy this value, and I got the Hausdorff under Mon-AI this value, and both are exactly same. And so the next thing I'm going to do between to compare the efficiency of executing the same code under SciPy and under Mon-AI, and check which one is which one runs faster. So the classical way to check efficiency I will use is with the time module. So import time, then start equal to time dot time for I in range 100. Calculate calculate under SciPy. Let's give it pred then ground truth gt vector and max distance. and here is CIPY, SciPy, time taken under SciPy, time under, just name it SciPy time is CIPY, SciPy time equal to time dot time minus strt, and print just print this time itself, SCIPY, SciPy time. All right, I got 2.8322, and now let's do the same for my Mono. So okay, I need to get the start running. strt start equal to time dot time for I in range 100. Calculate under Mono, spread GT vector and max distance, and then my Mono time will be time dot time minus s start, and print Mono time. And look at this, I got such a smaller value for executing the same code under Mono. So let's just quickly check the ratio between them, that is how much more the Mono time is faster compared to the execution time of SciPy. So just do Mono time divided by, sorry, it would be, because the SciPy time is much larger, so it would be SCI SciPy time divided by Mono time. Yep, so my Mono time is almost 14 times faster. That is, the SciPy time took almost 14 times more to execute the same code. So that was all about calculating Hausdorff distance using the built-in methods of various packages. And now I'm going to do a very simple from scratch implementation of Hausdorff distance with PyTorch. So yeah, let's import torch first and then define my Hausdorff torch function. Def s also DORFF 2D, and let's name it torch because I'm going to use torch xy. It will take two vectors xy, make x and y float, so x equal to x dot equal to t. Similarly, y equal to y equal to y dot float. Now calculate a distance tensor between them. A distance tensor will be, I'm going to use torch.cdist, which is a metric for calculating distance between two tensor in torch. So torch.cdist, and to that I need to pass x, y, and a p-value. P-value actually is a metric for which kind of distance that I am trying to calculate. So right here we can see the documentation, and for the p-value, p-value for the norm, for the p-norm distance to calculate between each vector pair. So when I pass p equal to 2, that means it will be squared, that is it is a Euclidean distance. And if you're interested, you can just quickly check their official documentation. It says computes batched the p-norm distance between each pair of the two collections of row vectors. And what are my row vectors? x1 and x2. So x1 input tensor of shape b by p by m, and x2 is input tensor of shape b by r by m, and p value is the p norm distance to calculate between each vector pair. All right. So cdist, and then so from this I will get a distance tensor. And now let's quickly check. Um, Actually, I need to get the minimum value of this tensor. So value 1 will be equal to distance tensor along the axis of 2, because if I print this distance tensor, let me quickly show. If I print a distance tensor mean 2, sorry, actually let me print the whole distance tensor, then it will be more clear. But let me write the function first. Distance tensor, then along the axis, take the mean along the axis of 2. This will return both tensor and indices, and that's the reason I need to also take the 0th element from this, and then I have to apply max, and along the axis of 1, and I will, sorry, not 11, that's 1, keep dim, I will keep the keep dim equal to true, and I need to take the 0th element. So remember, originally I said that the Hausdorff distance is defined as a maximum of all the minimum distance between two curves. So in other words, the Hausdorff distance is the greatest of all the distances from a point in one set to the closest point in the other set. Similarly, I need value 2, value 2, which will be again just similarly distance tensor mean 1. This will be along the axis of 1, and 0 max keep dim will be true, TRUE, and take the 0th element. Now final value will be the concatenation of them, torch.cat. I have to pass a tuple of value 1 and value 2, and the final return value is just the max of this, RETURN equal to what I'm writing, value dot max along the axis of 1 and 0. All right, now let's create two random tensor. Let's do a equal to torch dot random rand n, and I will pass the shape of the random tensor that I will create 2, 3, 4, and also I create another tensor b, which will be torch. Actually, it will be just the same, and 2, 3, and 4. So if we print, let's print a and print b as well. Oh, I did not run the cell. Yep. Yeah, so these are my two randomly created tensor, and I am going to apply the Hausdorff method that I just defined here on these two tensor. So print HAUS DOR distances HAUS Hausdorff HAUSDORFF underscore 2D torch. To that I pass A and B. That's all. And that is my output from that. but looks like I made a mistake because this final tensor should have just two elements. So why I'm getting four elements, let me quickly debug. Um, so this is my value 1, value 2, which is applying the mean and then taking the max, and then I'm concatenating these two values. Oh, I did not mention the dimension across which it should be concatenated, and the dimension should be equal to 1. And that's why I think I got final 4 elements in the final output. So let's run it again. Yep, now it looks awesome. So I got just 2 elements in the final tensor, and this is my Hausdorff distance between these two random tensor that I created. And an obvious question may come to your mind, that why I got these two elements and not a single scalar value as my Hausdorff distance. Because here the way that I have defined this method, it will take as its input of the shape batch, height, width, and there is no channel. So in these two input tensor that I have passed to my Hausdorff 2D torch, the first dimension is batch, then height, then width, and the output as well, the dimension of the output will be the batch, because I have 2 as a number of batches, and that's why I'm getting these 2 elements in the final output. So actually this is one Hausdorff distance and this is another Hausdorff distance. Both are individually scalar value, but the function will return me both together because the output dimension would be the batch dimension. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in segmentation models, one of the most important and most common metric for your model performance is pixel accuracy, and basically it's simply the number of correctly predicted pixels divided by total number of pixels. So after an image segmentation model is trained and outputs a prediction, we need to evaluate how well the model performed. And this is usually done through 2 ways, which are pixel accuracy and intersection over union. And for implementing a very quick pixel accuracy method, this is what I would do. So here I'm using PyTorch, and this will be my method. Accuracy. It will take 2 input arguments. One is the prediction output, let's call that output, and other one is actually the ground truth, GT. So what I will do, because in this case we are only dealing with scalar values and we do not need the gradient tree of a PyTorch tensor, so I will start with torch.noGrad. Oh, sorry. Output will be equal to torch.argmax. Remember here I am these output and ground truth, they are actually the logit values, and I'm converting them to probabilities, so I need to make use of f.softmax, and I have to do it over dimension of 1. And my correct would be just where the predicted pixels are equal to the ground truth pixels. So I have to make use of torch.eq, and to that I will pass the output and also the ground truth. and take int of that. And then the accuracy will be actually I don't think torched if because I'm working with float. So correct.sum and divide that. Why? Okay, I have a extra r here, and I need to divide that by the total number of elements in the correct tensor. So because it's a tensor, it may be three-dimensional, four-dimensional tensor in case you have batch as well. So we cannot use just len of that tensor because that will return me only the length of the first dimension. So what I have to use is correct.numel and wrap this entire thing with a float, and that will be my return value. Also note that while pixel accuracy is an extremely easy method to code, it is strongly biased by the classes that take a large portion of the image. And so for imbalanced classes, these pixel accuracy is not a very effective metric. Imagine a dataset with two classes where one class is only 5% of the total pixels and the other class, for example, a background class in the images, is 95%. Now, you could have a model that does nothing at all except predicting background for all the pixels, and you would still have 95% pixel accuracy in this case. So obviously, when your dataset, the original training dataset, is hugely imbalanced, this pixel accuracy is not very significant, not very meaningful metric. All right, let's see what I mean by class imbalance. Let's say take a note of these image set. On the left, I have the actual images, and on the right, I have the segmented image or the mask of the image. And let's say you ran this image set through your segmentation model. The image on the right is a ground truth or the annotation, and your model is supposed to produce a result which is as close as this. That is, it should properly segment the images, and in this case what we are segmenting is ships in a satellite image. And let's say your segmentation model predicts the entire image as black in the background, like this third picture that you see right now. That's the result of your segmentation model's prediction. So basically, again, your model is supposed to predict this mask image, but actually it is predicting this completely wrong and completely black image as the prediction. But in this case, it will still be 95% accurate. And that's because in the original image, 95% of the image content was just background. So even if your prediction is predicting the entire image as black, it is still be predicting it will still be accurate 95%. That is, pixel accuracy will be 95%. So is there something wrong with our calculation? Nope, it's exactly right. It's just that one class in this case, that is a background, was 95% of the original image. So if the model classifies all pixels as that class, 95% of the pixel will still be classified accurately, while the other 5% will not. As a result, although your accuracy is a whopping 95%, your model is returning a completely useless prediction. And so I gave you this example just to illustrate that high pixel accuracy doesn't always imply superior segmentation ability, especially when your dataset, original training dataset, is highly imbalanced. This metric should not be given much weightage. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching. Hello, my name is Rohan-Paul, and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will implement mean intersection over union, or Mean-IoU. So mean intersection over union is a common evaluation metric for semantic image segmentation, which first computes the IOU for each semantic class and then computes the average over all the classes. And so this is the formula for calculating the IOU, which is true positive divided by true positive plus false negative plus false positive. And here, true positives are those pixels that belong to the class and are correctly predicted as that class. False negative are those pixels that belong to the class but are incorrectly predicted as a different class. And lastly, the false positives are those pixels that belong to a different class but are predicted as the class. Let's take a note of this image right here. So obviously the leftmost image of the dog is the original training image, and so I have then three masks, and the first mask over here is the expected mask because that exactly resembles the dog sleeping over here. Then I have this mask predicted from my model, and then the last one is actually showing the difference between the ground truth mask, that is this expected image, and the predicted mask. And note these three colors here: red, green, and yellow. So in this last image, all the true positives are indicated by the yellow pixel, false positive are indicated by the red pixels, and false negatives are indicated by the green pixel. And once we have these difference between the predicted and expected mask, we should be able to calculate the IOU, or intersection over union, by following these mathematical expression. And now the Mean-IoU, coming to the main point of this video, that is a Mean-IoU. So that's determined by these pseudocode. So for each class, calculate the total area of intersection and area of union over the entire data set. Then for each class, calculate the IOU, which will be the total area of intersection divided by total area of union. And then lastly, calculate the MIOU, or the Mean-IoU, as for each class, all the class together. And with that, now I'm going to implement a simple MIOU method with PyTorch. And also note that these IOU, or intersection over union, is a value between 0 and 100, where a larger value indicates a more accurate segmentation, and the MIOU is then the mean value across all the classes in the dataset. So first import torch. Also I need to import torch.nn.functional as f, and then my method def Mean-IoU, that will take a predicted label, then a label. It will take a small value for smoothing. I'm calling it epsilon or EPS. Let's give it 1e minus 10, and num classes. Let's just give a default value of 10. And because I do not need the gradient tree of PyTorch Tensor, so I will start a context manager with torch.noGrad. And I'm going to make use of Softmax over here, and that's because these predictions of your model, that is this predicted label, will be in one hot encoded form. So first, I'm taking Softmax, if your model already is not taking the Softmax, to get some probability. So that would be f.softmax predicted label dim equal to 1. And then after taking the softmax, I need to follow it with the argmax to get the index with the highest probability at each pixel. Predicted label, oops, sorry, predicted, I just want to have predicted label equal to dot max. That will be predicted label across bin 1. And then I'm going to make use of torch.contiguous to make my to create a copy of my tensor, and where the elements will be in a contiguous fashion. So predicted label equal to predicted label dot contiguous pi minus 1. I have to do the same for the label vector as well. Contiguous minus 1. Now let's define a list variable to hold the IOU for each single class. So SINGLA plus would be, yep, for class number in range. I'm starting a loop from 0 up to class number, and my number of class is coming from my this argument num classes. And this is very much where I'm looping per pixel class. And inside the loop, my true predicted will be true predicted class actually. That will be where predicted label is equal to class number. That's my true predicted class, and true label would be where label equal to class number as well. Now if true label dot long dot sum, I'm chaining few methods here, dot item will just extract the value from the tensor. If true, spelling mistake, true label equal to 0, that is no existing label in this loop, then my IOU single class dot append will be in p dot, I'm going to use not a number, man. I have not imported numpy. Let's do that. All right. And now I have that condition fulfilled. So if that is not the case, else my intersection, okay, now let me think. Yeah, in this case my intersection will be torch dot logical and that will take true predicted class, then it will also take true label, and then I have to do sum dot float dot item, and my union will be torch.logical or, and that I will pass true predicted class true label sum.float.item. All right. Now my IOU will just be the division between these two numbers, but of course I have to adjust it with my epsilon value for smoothing. So that would be intersection plus EPS divided by union plus EPS. And I also need to append this IOU to single class.append IOU. Cool. So I can come out of the loop and I can return the average of all these, which will be np.nan mean IOU single class. Now, couple of points to mention here. This method right here, contiguous. Note that it returns a contiguous in-memory tensor containing the same data as self tensor. If self tensor is already in the specified memory format, this function returns a self tensor itself. Now, tensor.contiguous will create a copy of the tensor, and the element in the copy will be stored in the memory in a contiguous way. Means the order of its elements in memory is the same as if it had been created from scratch with the same data. The contiguous function is usually required when we first use transpose on a tensor, and then we view or reshape it. Now, also I want to mention about these function logical and also logical or. So logical and computes element wise logical AND of the given tensor. Zeros are treated as false and non-zeros are treated as true. And I did it here, that is logical AND here, to find where prediction and target are equal between two input tensors. Note here that the two input tensors themselves consist of true false, that is Boolean type. So this was just one way to write this method to calculate the mean IOU, and while the concept remains same, that is underlying mathematics remains same, you can write mean IOU method in slightly different ways. Actually, if you go through many GitHub repositories or many others code who have implemented this mean IOU in various section with either Numpy or PyTorch, you will find slightly different ways to write this up. So I'm also going to use a slightly different style to do my mean IOU calculation. So just write another method here. So this is just alternative way to calculate IOU. Sorry, mean IOU. Alternative mean IOU calculation. So my second function, let's name it as mean IOU. It will take a target and also predicted. Now I'll do slight assertion testing at the very first step. If target.shape not equal to predicted.shape, then target, sorry, where as function RGET target dot shape, and also predicted values have SLP shape predicted dot shape, and then just put return. Also, another assertion test, if because I'm dealing with PyTorch image dataset here, and I'm expecting the dataset will have 4 dimension, that is batch size, channel height, width. So I am going to do target.beam not equal to 4, sorry, not equal to 4. In that case, print target has been it must be 4. Return. And now my final actual calculation of IOU. So let's define the term IOU sum equal to 0. Run a loop for I in range target.shape 0. And now I'm going to make use of slice notation to include all the dimension, all the elements of each of the dimension after the first one. So that will be 1 slice, 2 slice, 3 slice. And now I'll be chaining together few methods: clone dot detach to detach the gradients tree, CPU, taking all calculation to the CPU dot numpy, and then finally argmax. I got to do the same for the predicted value as well. So let's just do predicted. Where is my, what was the name of, so that's predicted. Yeah, let's call it predicted, or then it will be predicted. Otherwise, the rest everything will remain just the same. All right, now intersection is equal to np dot logical end. To that I'll pass target ARR, then predicted ARR dot sum, and union will be np dot logical or target array and predicted array dot sum. Now another little assertion test before the final calculation. If union equal to actually equal to 0, in that case just return IOU score as 0. Score as 0. Because in that case there is no union at all. Else IOU score will be equal to intersection by union. Now I can come out of the loop and IO update my IOU sum plus equal to IOU score. And finally, my MIOU, that is Mean-IoU, will be IOU sum divided by target.shape0 and return MIOU. So that was two alternative way to do this calculation of Mean-IoU, and now the final and the third alternative way, because till now we used mostly PyTorch kind for both of these methods we used PyTorch as an underlying framework that I'm using to build this. But now in the third alternative I will use pure sklearn, scikit-learn. Third alternative to build MIOU. All right, let's do this. Div. Okay, first I need to import scikit-learn. From sklearn dot matrix import. I need confusion matrix because that will give me the matrix containing the true positives and true negatives, all these things. And now my method, div Mean-IoU. So I will have y prediction and y true. Now first I'm going to flatten these vectors, so y pred will become y pred dot flatten. Similarly, y true will become y true dot flatten. And now my confusion matrix should give me the matrix containing. Now before doing the confusion matrix, quickly check the definition. So here I am in scikit-learn's confusion matrix official documentation. So it computes the confusion matrix to evaluate the accuracy of a classification. By definition, confusion matrix C is such that Cij is equal to the number of observations known to be in the group I and predicted to be in group J. So this is the key thing. And if I go to, so it will take y true, y pred, and it will also take another argument labels, which is an array-like of shape, number of classes, and default is none. So the return value from the confusion matrix is a matrix which is of nd array of shape n classes by n classes. So confusion matrix whose this is a matrix whose ith row and jth column entry indicates a number of samples with true label being ith class and predicted label being jth class. And that's all I need, because once I get this matrix, then from this matrix along the diagonal I will get my intersection points. Yeah, so let's actually just go and start coding, then it will be it will make sense. Confusion matrix will become, actually what I'm doing, confusion matrix will give me y true, then y pred. I also need to pass a label ceiling because here my labels are binary 0 1. Actually, to avoid some ambiguity, let's name these confusion tensor. All right, now what I'm going to do, compute the mean IOU. So for that, I first need the intersection points. So my intersection will be equal to np.diag. Again, if I go to the official documentation of np.diag, so this extracts a diagonal or construct a diagonal array, and then it says see the more detailed documentation for numpy.diagonal. If you use this function to extract a diagonal and wish to write to the resulting array, so parameters, it takes v array like k, an integer. All right, and what does it return? It returns the extracted diagonal or constructed diagonal array. So if we see an example, first here there is an example. First, they're building a matrix with np.a range 9 reshape 3 by 3. So this is the matrix that we just built with this code here, and now my diagonal will be this number 048, that is they are along these diagonal. And once I do np.diag x, I get the output array as 048. That's the vector I get, and that's what I want for my intersection, because here, here, and here, the prediction and the true labels are actually equal, and that's what I want. For example, if you can see in this matrix right here, the row number here is 2 and the column number here is 2. So row number 2 and row number 2 and column number 2 matches in this place. Similarly, row number 1 and column number 1 matches in this position. So along the diagonal I get my intersection points. So that's what I want. np.diag and confusion tensor. Oops. FU confusion tensor. And then my ground truth set will be ground set will be confusion tensor dot sum along axis of 1. That will be my ground truth set. And similarly, my predicted sets will be confusion tensor dot sum x is equal to 0 along the rows, that is. And now union will simply be my ground truth set plus predicted set minus the common area, which is intersection. Otherwise I'll be counting intersection twice. So ground truth set plus predicted set, from there I minus a deduct intersection. Finally, IOU is equal to intersection divided by union dot s type np dot float 32. All right, return. What do I return? I need to take the average of all these. So np dot mean IOU. Perfect. Let's quickly see an example of this. So what I will do is, second, let me copy this thing, and oh, I need to copy import. That is only I'm copying only the third alternative to build MIOU. So I'm going to a Jupyter notebook and just pasting that code. Let's just, am I in a code cell? Yes, let's just run it. I just want to see a use case of this method that it's actually working. Okay, I need to import Numpy as NP. All right, now I'm just going to define two basic metrics with np.aray. Let's give inside this one, and I also need to define y, the second set of y, which is y predicted. np.aray. All right. And now what I will do is Mean-IoU to that. I will pass y true. Sorry, first one. What was the first argument? Y pred. Yeah. So give y pred and y true. Let's run it. NP is not defined. Okay, define it. And now run it again. And there I go. So that's a value for my mean intersection over union. So yeah, what we did basically, three alternative ways to build the Mean-IoU, which is a very important metric in object detection and semantic segmentation problems. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching. Alright, that pretty much wraps about this video. If you liked it, do smash the like button. And also don't forget to subscribe, because I'm doing 5 to 6 videos each week. So see you in the next one, and thank you very much for watching.